and welcome to this morning's, as we call it, a reconference webinar at Impala. Now, what this means is that the presentations that we will hear today were presented previously at conferences through SAIMM. And as an Impala group, we've put some of these presentations together to be presented to the Impala group as a pre-conference. Yeah, you all should know by now that Impala is a corporate sponsor, a corporate partner of SAIMM, and this is the reason we can do things like this. We work together to bring the knowledge to our team members. And we also know that these circumstances these days, it is very difficult to travel, and it is also very difficult to attend all these conferences and seminars. And this is why we're bringing it home, in this format. So again, welcome to this conference. To start, I suppose, with a value moment, as we do it traditionally in our group. I would like to leave this message with each one of you today. Let's never stop learning. Let's grow ourselves each and every day. And hopefully this conference will help us in doing that. If each one of us can take one or two things away from this morning that we didn't know before, then this would definitely be a success. So let's continue learning, even if we 98 years old and sitting in our rocking chair somewhere. Let's keep on learning and keep the mind active. On that note, I would like to welcome our first presenter, and I'm going to read to you his short CV, short resume. Our first presentation, the heading is PGM Furnace Crucible Upgrade and Performance. And our presenter, Hugo Joubert. Hugo, welcome, and thank you for making time for this. We all know that it is difficult, to make time for things like this, and you just said that you will do this. So thank you for that. So Hugo Joubert is a mechanical engineer with 30 years furnace and smelter design experience, working in numerous roles in production, technical development, and business development. He specializes in furnace equipment design and solution development. Hugo started his career as a plant engineer on iron blast furnaces in South Africa and completed his master's degree part-time on furnace lining cooling system design. He then joined Tailings Pyrometallurgy in 1998 as a design engineer. In 2000, he saw the light and completed his diploma in pyrometallurgy at Wits University. Hugo joined Xstrata in 2008 as an engineering manager before he joined Tailings in 2015. His expertise includes electric furnace as well as stop submerged lance furnace technology. He is currently the general manager responsible for base metals at Tailings Pyrometallurgy. Before Hugo starts, I can just also highlight to everyone online, if you have a question to Hugo, please, you will not be able to speak, but you can type your question in the Q&A area so that we can just at least read your question, and then Hugo will then respond to your question in that format. On that note, then, Hugo, the floor is yours, and welcome again. Thank you.
Thank you, Adele. Just to check, everybody can hear me? Can you guys hear me?
Yes, we can definitely.
Okay, fantastic. And am I sharing the right screen?
You are sharing notes at the moment. Sorry, Adele, you are sharing notes.
Okay.
So if you just want to change your display settings.
Yep. Let's see if that works.
Awesome. Perfect.
That works. Thank you.
Okay, fantastic. So good morning, everyone, and yeah, thank you very much for this opportunity. It's great. So as Adele said, I did this presentation, this paper, presented it at the Southern African Pyrometallurgy Conference. And it's about the Sibanye Furnace 1 crucible upgrade that we did a couple of years ago. But before I start, let me just also acknowledge my co-authors, Gerrit de Villiers, Johan Nel, and Derek Senecal, also from Tanaba Pyromet, and then Fariso and Betsy and John Davies from Sibanye Stillwater. So why is this not flicking over? Sorry, just give it a moment. Seems like it's taking its time. Guys, just hang on. It seems like my PowerPoint is just not working with me this morning.
No worries, Hugo. You know Murphy, nee?
Now it wants to restart my whole PowerPoint. What the hell is going on?
Yeah, because
That's Microsoft.
we're currently seeing your power. Yeah.
Okay,
Not seeing
sorry
anything
guys,
now.
let me just try that again. It seems like it's just restarting everything. I'll get there. Let's try that again. Okay, let me see. Tell me when you guys can see it.
I can see your presentation, but not in presentation mode. So I see your PowerPoint.
Sure, and now I have to switch it again.
Yes, you need to switch.
Okay. Well, let's see if it
Perfect.
changes. Now, there we go. Okay,
There we
it's working now. It seems like Microsoft just decided it wants to close the whole PowerPoint and restart it again for some reason. Okay, so first start by giving you an overview of the plant and the project itself, and then talk about some of the key design changes that form part of the crucible upgrade, and then talk a bit about the project implementation and the performance to date. So the Sibanye Stillwater Marikana smelter, I'm sure many of you are familiar with it. It consists of it has 5 electric furnaces, 3 P.S. Smith converters. Furnace 1 and 2 are the main production units, and then furnace 3, 4, and 5 are used on a standby basis. So furnace 1 was originally commissioned back in 2002, but then due to ongoing issues with furnace containment, Sibanye approached the market in 2020 to try and find a permanent solution or some permanent solutions to the issues they have. And based on what Tanaba put on the table, they selected us to do the crucible upgrade. Started the project in May 2021, and we tapped the first mat in September 2022. So the main objectives of the crucible upgrade was to improve the campaign life and to improve the long-term availability of the furnace. The key design changes that form part of the crucible upgrade are increase in crucible diameter, a lifting of the mat tappel above the skew back area, half design, complete new half design, a lower sidewall graphite backlining. I'll talk a bit about that. And then our new composite copper graphite cooler design for the slag sidewall. So the mat tappel design is based on a mat tappel design that we did for furnace number 2 at Sibanye back in 2012, and it has been very successful. So the request was to use exactly the same design. It consists of 2 water-cooled copper tappel blocks, and then on the outside we have an uncooled meionite faceplate. So this is actually a newer development that we did in 2018 for them. Again, this is working really well, and it's used on furnace 2 and furnace 1 now. One of the issues that we had with the tappel design on furnace number 2 is the fact that your tappel sits in your skew back, basically. So the tappel center line is in line with the top of the skew backs or skew bricks. As a result, any thermal expansion in your hearth impacted directly onto your mat tappel, and that caused distortion of the mat tappel bricks and the mat tappel itself, as well as distortion of the very key lintels above the mat tappel. So what we did for furnace number 1 is we lifted this mat tappel now completely out and above the skew brick area. And as you can imagine, one of the big advantages, if you do have your thermal expansion of the hearth now, your skew bricks are more likely to slide underneath, if I call it like that, so underneath your mat table, and you have less distortion taking place in your mat table itself. Another big advantage is that you end up with a much deeper mat bath that's maintained underneath the mat table. So the advantage of this is it acts like almost like a thermal flywheel, and it helps to reduce the thermal cycling in the hearth bricks as well as the critical skew brick area. Also on the hearth design, what we did is we designed it to maintain the mat solid at temperature or isotherm above the bottom of your working lining. That is the bottom of the working lining, and that mat solid at isotherm we estimated would be 200 millimeters above that. And the reason for that is if you do get mat penetration in the hearth, is to make sure it will freeze before it gets to the bottom of your working lining. So another important design change is on the lower sidewall area. Of course, this is a very critical area. We have both mat and slag in the tidal zone. Both the mat and slag in these furnaces are extremely aggressive to the macro bricks that we use, even if it's high-grade bricks. And as you probably know as well, we have a very high superheat of about 600 degrees Celsius in our mat. And in this lower sidewall area, we prefer not to have any water-cooled copper, just from a safety point of view. So the design that we implemented is what we developed also for furnace number 2 at Cabana, and it's been working there now for 12 years very well. It consists of your working lining and then a back lining that's basically graphite against a furnace shell with forced air cooling on the outside. And the idea is to extract all the excess heat from your working lining in this critical area. So if we move up to the upper sidewall, of course, I think you are all familiar with this, the chloride accelerated sulfidation issue. It's quite unique to the PGM industry in South Africa. Basically, where you have your concentrate layer and your slag tidal zone, you have some sulfur coming off your concentrate layer, condenses on copper coolers in your sidewall, reacts with the copper, forms copper sulfide, which is the corrosion product. And that's how you wear it. And it's also been found to be accelerated in the presence of chloride-bearing species. So this photo shows a plate cooler from furnace number 2 at Sibanye after 27 months of operation. And you can see how it's been corroded away, especially on the hot face, formed almost like a knife edge. And you can just imagine what this does for the thermal contact between the cooler and the surrounding brickwork, and it just completely takes away any of the cooling efficiency. This is a photo of another plate cooler showing the different corrosion products. The black is your copper sulfide mostly, the green is copper hydroxychloride, and then you can see there's some yellow patches where you have freshly condensed sulfur on the plate cooler. So we explored quite a few different ways or potential solutions to prevent sulfidation from taking place. One is calorizing. We did a lot of test work, showed a lot of promise. Unfortunately, it didn't perform so well in the furnace itself. Hastelloy weld layer, that's something that we still use. It's quite successful. And we use it on the plate coolers on furnace number 2 now, as well as the slag tappel blocks for furnace 2 and for furnace 1. However, it's difficult to apply the Hastelloy on the whole cooler and cover the whole cooler surface area. So we decided to go for the option of using graphite. We actually have a patent dating from 2006, covering the use of graphite combined with copper, specifically for this issue. In short, your copper keeps the graphite cool enough so it doesn't oxidize, and in turn, your graphite protects the copper from sulfidation, basically prevents the sulfur from getting to the copper. We first implemented this in 2017 on the Mexico copper coolers installed at Northern Platinum furnace number 2. Here you can see the copper at the back, and this is the graphite on hot phase dovetailing onto the copper. And these coolers have now been in operation for 6.5 years. We actually started this week with a rebuild on furnace number 2 at Northern, and all these coolers are being removed at the moment, and they're going to Tospeki, where they will be cleaned up, and we will inspect them and see how many of them we can reuse again. One of the issues we did pick up here is that you do still get sulfur coming in between the adjacent coolers, and then it attacks the copper behind the graphite. So what we did for furnace 1 for this upgrade is we developed a composite copper graphite cooler that combines copper plate coolers with graphite. And what is unique about this design, that the Nova design, is that the graphite not only covers the hot face of the copper, but it also completely covers the top, the bottom, and the sides of the copper, as you can see in this composite cooler design. So there's no way for the sulfur to get to the copper. We did extensive test work beforehand on this composite cooler to confirm the constructability, the cooling efficiency, as well as the durability. And you can see we're installing 2 rows of these coolers on top of each other. We have a vertical hold-down mechanism to ensure that you don't form horizontal gaps between the coolers, as well as between the bottom coolers and the refractory lining below. The coolers are designed that you can actually install individual coolers and remove individual coolers from the outside of the furnace. And we use our external containment system to cover all the interfaces between adjacent coolers, vertical and horizontal, as well as between the bottom cooler row and the refractory lining below. So just quickly on the project implementation, project started in 2021. It was quite ambitious, May 2021. By April 2022, we switched out the furnace, and by August 2022, we switched the furnace back in. And then the first mat was tapped in September 2022, and by November 2022, we achieved our nominal 15 megawatt power inputs on a consistent basis. So looking at the performance, so looking first at the half center temperatures and heat flux, the light blue line there indicates the power input. So you can, this is for June 2023, last year, so it's a year ago now. The furnace was operating at 8 or 9 months by that time. So there's a 15 megawatts, most of the time just above it. If you look at the red line, it indicates the heat flux in the center of the hearth, and that was on average about 3.1 kilowatts per square meter, which is in line with what we estimated. The hot phase temperature of the hearth is lower than what we anticipated, and we believe this is due to the deeper mat bath that we have inside of the furnace due to the lifting of those mat apples. Ineffective, it's because you're keeping your electrode tips further away from the half hot phase. And then if you look at the blue or the navy line here, that is the mat solidus isotherm position above the bottom of the working lining, and we settled about 210 millimeters above it compared to the 200 that we originally estimated. Another very positive consequence of this design is the skew brick radial movements. So following the initial heat up of the furnace, you can see these skew bricks completely stabilized. So Sibanye is actually really good at monitoring the skew brick positions on a regular basis around the circumference of the furnace and looking at the radial movement outwards. And you can see it completely stabilized inside the furnace. This is all the way to November, end of November last year. And this is compared to previous campaigns where the radial movement continued to take place throughout the campaign. And again, we believe this is the main reason for this is that lifted mat tappel, and as I discussed previously, that almost like a thermal flywheel effect that you have, reducing the thermal cycling in the hearth bricks as well as the skew bricks. Another very positive consequence is the mat tapping temperatures. the slag temperatures are the same as what they had in previous campaigns, nothing different. They're not feeding a different concentrate, but their matte tapping temperatures are on average about 50 degrees Celsius lower compared to the previous campaigns. And again, we believe this is the main reason for this is the increased hearth diameter or crucible diameter, combined with this deeper matte bath that's maintained below the matte tapple, that results in a lower average matte tapping temperature. So looking at the cycle where we installed the composite coolers, again, this is for June 2023. Again, the red line here indicates the power input into the furnace, just about 15 megawatts. The blue line there indicates the average heat flux around the circumference of the furnace. It's settled at about 27 to 28 kilowatts per square meter, which is lower than the design base maximum. And then the green line indicates the temperature, copper temperature that we measure, and the bottom copper plate cooler in the bottom row of composite coolers. You can see that settled at about 170 degrees Celsius here compared to, it's much lower than what we achieved during the test. This graph also shows the heat flux around the circumference of the furnace through the composite cooler sidewall. The blue line indicates the 50th percentile around the circumference between 20 and 40 kilowatts per square meter. And the red indicates the 99th percentile between 35 and 60 kilowatts per square meter. And again, that's lower than the design base maximum and quite a bit lower than what we achieved as a maximum during the test work. So these pictures were taken December 23, so just last December. Furnace has been in operation for 14 months by then. And but it looks the same today. It still looked extremely well on the outside. There's absolutely no sign of sulfidation on any of the copper coolers, and no differential movement between adjacent coolers and between the coolers and the refractory lining below. This photo is from January this year, 24, during a matte tapple repair when they lowered the slag bath. Gives us a really good opportunity to inspect the hot face of the composite coolers. You can see there's some frozen slag on there, but where the graphite is exposed, you could still see the machine grooves in the graphite, so no signs of wear on the graphite hot face. So in conclusion, we were awarded the contract in May 2021. First matte was tapped in September 22. The main objectives were to improve campaign life and availability, increased crucible diameter, help to lower the power density, and importantly, lower the matte tapping temperatures. The elevated matte tapple, I think that was really crucial. Again, I think that played a role in lowering the hearth and matte temperatures. But very importantly, it reduced the hearth and skew thermal cycling and resulted in much more stable skew bricks. And then finally, the composite copper graphite coolers, the temperatures and heat fluxes are within the design limits. And to date, there's been no sign of sulfidation, graphite wear, or differential movements. Yeah, so thank you very much. And any questions, I'm available.
Yeah, thank you. Thank you, Ihu. It was quite informing. I don't see any questions from our Q&A section. Am I right in saying that, Camilla?
Yes, there are no questions in the Q&A.
There are no questions. I think from my side, Ihu, lifting the matte tapple has been the discussion in PGM furnaces in the last, let's say, 4 years, and or if not a bit longer. And with that came quite a few benefits, and you've highlighted that as well. In your experience, are there any negatives in lifting the matte tapple? Because historically, it was placed for a reason where it was placed. And in the last, let's say the last decade, it became quite, highlighted that all PGM, furnaces in the industry, that is the next phase. Lift for the right reasons, for what you exactly said. In your opinion, then, what will you say is the negatives, and why would that have been designed originally in the way it was? Or are we missing something?
Yeah. Look, I think, Adele, I can think of 3 reasons why it was done originally like it was done. The one is, of course, all to do with the bean counters. So they don't like the fact that we hold up so much matte and PGMs in the furnace. I think that was probably the biggest reason. That's the one that was always given. From a technical point of view, if you have so much matte in your furnace, when you then get to the point where you need to replace your half, okay? We think it's going to happen in 12 years' time. We're going to replace the half. Then you need to get rid of that matte. You need to get that stuff out of the furnace. So what we've designed the furnace to have a place for a salamander tapple, which is quite common, what they use on blast furnaces, the iron and steel industry, for example. So you can just drill basically through the side of the hearth and you empty your furnace if you know you're going to replace your hearth in any case. And I would say that third thing that you need to think carefully about is the effect on that lower sidewall area. Because we don't like to put copper cooling in that lower sidewall, as I discussed. So you need to design it very carefully to make sure that the wear there is not going to be, or the wear rate is not going to be too high. And that's quite important because we know that, in most processed slag is the most aggressive to these bricks. But with these PGM furnaces and this very high superheat in the matte itself is also extremely aggressive to these bricks. But that design with the graphite, it works very well. 2012, we did extensive test work with Sibanye or Lonman back then to understand the effect on the graphite and its resistance to the matte as well as to the slag. And we did a number of pot tests and etc. And it performed exceptionally well. So we're quite confident that this design works well.
Oh, thank you for that. We have a question from Bishan. He would like to know, can you please quantify the benefit of the Hastelloy coating?
Yes, absolutely. So, Bishan, I would say the Hastelloy coating, I can actually show you some pictures. I just don't have them ready now. We've already tested them on some of the plate coolers on furnace number 2, and it's amazing. It just you don't get the sulfidation. It does not go through the Hastelloy layer. So it's quite interesting. Because we only cover the first 100 millimeters of these plate coolers of the Hastelloy because it's really expensive as well. Plus, we now have to machine it as well because we want to maintain a good interface between the cooler and the refractories around it. So you have to machine it all nice and flat. But to machine that stuff, it's extremely difficult and expensive. And that's why we limit the area that we cover. But it's actually quite interesting to see what this plate cooler looks like now when it comes out after 27 months in furnace number 2. You still see the Hastelloy front part is perfect, but then the plate cooler behind the Hastelloy, the back part of the plate cooler is completely corroded away. So the Hastelloy definitely works to prevent the sulfidation from taking place. I hope that answers your question.
Thank you, Hugh. Then we have one hand raised, and we allowed Louis to speak. Normally we don't do it that way. We normally go to question and answers. But Louis, we allow you to speak. So please, you can ask your question. You unmute, Louis.
Hi, Adele, can you hear me?
We can hear you.
Awesome. You can hear me?
Yes, we can.
Yeah, morning to you, Hugo. Morning, Adele, and morning to the team. Yeah, I was trying to type my questions here. If Hugo you can explain to us your experiences with your, I know it's a circular furnace here, your electrode PCD to the wear profile, especially on your med tables. I know there are some factors to be considered. Yes. I know when you get to the 16 line, again, industry experience has shown that we need to pay particular attention the electrode to taper distance there. If you can sort of elaborate for us more in terms of the experiences there.
Absolutely. No, thanks for that question, Louis. So I think we all read a very good paper that was presented by the guys from Anglo, Lloyd and Rodney and Kevin. In 2015, they presented that paper looking at the sizing of the furnace and understanding what the effect is on the matte apples and the changes they made at Polokwane on the 6-9 furnace. And we listened to that. So when we resized this furnace number 1, that was one of the key things we looked at. We not only looked at the half power density, we also looked at the linear power density between the electrodes and the matte apples. And in short, we redesigned or we resized the furnace to also keep the linear power density below 1,500 kilowatts per meter. That's between the outside of the electrode and the matte apple sidewall. So and it's very important that because in these furnaces, all your heat goes in via I2R heating in your slag bath. And then your matte is basically heated up from your slag. So it's convection from your slag. And of course, the matte comes out of your slag. So that's where that heat comes from. And if you can increase that distance, the further out it comes, especially in the circular furnace, that the convection becomes weaker towards the sidewall. And if you increase the diameter, it's even more weaker. And it does have an effect on the matte temperatures, as we've also seen now on this furnace. We believe that's the main reason for the lower matte temperatures is this increased diameter as well, and the distance between the electrodes and the sidewall. I hope that answers your question.
Yeah, thanks, Hugo. Thanks, it certainly does.
Thank you, Louis. Yeah, guys. Unfortunately, we ran out of time for this portion. So the questions I see, there's another question from Mlu. We will come back to you on that question. Mlu, we will ask Hugo to just write a reply on your question. But unfortunately, our program moves on, and before we could continue, Hugo, again, thank you so much. We do appreciate this, and I'm sure you've prompted a few minds now with questions. And these guys, I'm sure you are available for questions going forward if need be. Thank you so much.
Thanks, Adele. And yeah, can I ask if you could just send the questions to me? I don't know if it's going to still be available once I finish here.
Definitely.
If you can,
we will send it to you for formal reply. Then we can put it to the audience. Perfect.
Yes.
Thank you.
And if anybody else have more questions and I want to send me an email, they're welcome to do it.
Perfect. Thank you, Hugo. All right, guys, we now need to move on to our next topic, and this is very close to our very close to home and to our hearts. And this is actually a project that was done for our Zimplats operation, and it will be quite good to listen to the outcome of this. Our presenter is Tasneem Isaacs, and she is from Hatch. I'm going to read a short resume. Tasneem is an exiled candidate engineer with 3 years experience as a consultant in the PGM industry. She works in the industrial clean tech unit with the metal sector at Hatch that specializes in pyromet processing of metals and handling and treatment of smelter off-gas. She has experience in pre-feasibility, feasibility, and execution phases of the project life cycle, and do process mapping and design validation. Tasneem, welcome, and thank you for presenting live this morning. It's always nice to have someone presenting live that can answer questions immediately. All right, so Tasneem is presenting to us the converter aisle scheduling using dynamic simulation, and as I indicated, the simulation is done for our Zimplats operation, specifically linked to our new furnace that will be starting up very, very soon. On that note, Tasneem, I'm handing over to you. Thank you.
Thank you so much for the introduction, Adele. Good morning, all. Just bear with me while I share my screen. Okay. Okay. Can everyone see my screen in presenter mode?
Perfect.
Okay, perfect. Just give me a second. Okay. So as my introduction, my name is Tasneem Isaacs, and I'll be presenting on my paper, Convertile Scheduling Using Dynamic Simulation. Before I start, I'd like to thank my co-authors, Johan Bezeidenhout, Bettine Gerrits, and Stanley Matutu from Simplats. Without them, this work would not have been possible. Okay. So starting with the agenda, I'll take you through the introduction and Convertile project background, why we've chosen dynamic simulation to investigate a complex system. Then we look at the methodology and approach to the simulation, then dive into the project outcomes. Finally, we'll end off with the key takeaways of the project in the form of our conclusion. So Zimplats expansion of the smelter at the Selous Metallurgical Complex will see an increase in concentrate throughput by 250%. The expansion includes a new hatch, 6 inline rectangular furnace, 2 12 by 24 Pier Smith converters, a second AL crane to service these new units, a new converter flux and rivets feeding system, and the new 21-ton ladle fleet. So here's a view of the converter aisle layout. On the right over here, you'll see the current operation has an existing round furnace, the two 10 by 15 Pier Smith converters, 1 aisle crane, the 12-ton ladle fleet, and the converter matte wet granulation facility at the far east end of the aisle, with the capacity to process the current daily converter matte production. So during normal operation, only one converter operates with the return of hot converter slag to furnace 1 without any constraints. The expansion is then extended to the west end of the aisle to accommodate for the new furnace, the 2 12 by 24 Pier Smith converters with the new second aisle gantry crane and the new 21-ton ladle fleet to replace the old 12-ton ladle fleet. So the current matte granulation facility must also undergo equipment and capacity upgrades in response to the expansion. And then a space has also been allocated between the west and east end for future converter number 3 over here. So the final expansion will see the operation of the 2 furnaces and 2 large converters in operation at a time. With the expansion, however, the aisle will see significantly more movement and activity while introducing constraints not experienced before in the aisle. These include matte tapping, scheduling of the 2 furnaces to charge the converters, furnace inventory management, converter scheduling, converter preparation, ladle management, the 2 crane interaction with a center-to-center distance constraint of 17.3 meters to maintain the structural integrity of the aisle. We have the hot converter slag return to the furnaces with the constraint that slag cannot be returned to furnace 2 while operators are on the matte tap floor. And then consideration of the impact of layout on the operation and many more. While all these new design, logistical, and operational factors make it then difficult to predict our performance using static calculations like Excel. So we needed to look to a tool that would allow us to understand the impact of our logistical constraints on the smelter throughput and validate the process design. So this brings us to dynamic simulation. So dynamic simulation allows us for time-dependent analysis of complex and variable interactions within a process. This allows us to better understand the dynamic interdependencies and logistical constraints on the overall throughput and operation, as well as identify any potential design limitations before project implementation. So inputs to the dynamic simulation in model include engineering specifications based on the project design as per hatch design, the operating data, which may be in the form of log sheets and operational practices as per client guidance. And then the operational data specifically allows for the incorporation of process variability that is inherent in the process. So this allows us then to study constraints and identify worst case scenarios. So these inputs allow for the development of a model that mimics dynamic behavior over time. And for our modeling, we've used Simio, which is a simulation, production planning, and scheduling software. So I want to take a moment to run through a model preview with you guys. You'll see the layout of the model is exactly as the owl layout shown before. For the first part, you'll see the 2 furnaces and 2 large converters operational as per the colored units over here. Note that the 2 small converters operate as 1 large converter for the expansion. See how the model tracks the furnace inventories for the matte and slag on top over here, as well as the converter bath levels down here. It also tracks the intercrane distance when a furnace is tapping matte, and schedules which converter you should charge to. So then also look at how the 2 cranes respond to the converter owl requests. These rectangular boxes over here that light up as a crane enters it represents a zone. We've ensured that 2 cranes will not violate the distance constraint mentioned before by stipulating that 2 cranes cannot operate in the same zone at the same time. There's so much more to this model, but unfortunately our time constraints. So basically from the model performance, we can plan production, diagnose the operation, and quantify equipment utilization, etc. Yeah. So then moving on to the methodology and approach. So once we've defined what questions we want answered, the battery limits and scope of the study, the modeling approach was then to keep the model as simple as possible while maintaining an accurate representation of the converter operation and ensuring predictive validity as well. So the dynamic simulation modeling scope was approached in 2 steps. Step 1 was to model the existing converter aisle as seen in the reddish boundary over here. This was to develop a base case that was representative of the current aisle operations and to confirm certain modeling assumptions that we've made. So once the model was validated and there was confidence that the model could represent the aisle operations, the model was further developed to include the future expansion as now seen in the blue boundary. So once the model was built, we could then derive full value from modeling through scenario analysis. What if experimentation was easily carried out, promoting a greater understanding of our capabilities and limitations? The model outcomes were then key to drive decision making. So let's look at a few of those outcomes. So firstly, we'll explore how the model helped confirm some key design parameters and achievability of our throughput capacity according to the project design. Then we'll touch on a design bottleneck that the model highlighted. We'll follow up with confirming the aisle's ability to achieve catch-up capacity. And then finally look at one what-if analysis for potential capital optimization. So in your top left corner, you'll see key throughput and production performance indicators, namely concentrate feed, furnace matte, and the final converter matte product. The model confirms that the product design does allow for the expanded aisle to meet the production targets given all the logistical constraints in the aisle. So let's move it over to the furnace matte inventory. So given the tight coupling of the furnace and converter operations, it is crucial to understand the behavior of the furnace matte levels with the idea to prevent the furnace from reaching that maximum matte levels. So the graph displayed in front of you shows an hourly run chart of furnace 2 matte levels for 1 operational year. The minimal operating level is at 402 millimeters at tap-hole elevation, blue line showing the nominal level, and then the reddish line showing the maximum operating level. So what's interesting in this graph is that we are seeing how the matte levels harmonize with the converters rising and then dropping as it taps to a ladle. Note also how it responds to process upsets or downtimes downstream, as seen when the furnace reaches that maximum matte level. So through this, we could gain insights into furnace behavior and validate the new furnace 2 design. Then another important design consideration is the number of matte taps per day. The graph in front of you shows the frequency of matte taps per day for furnace 1 and furnace 2. So matte tapping activity includes when the operator is on the tap floor, when they're opening the tap hole, tapping via the mat launder, and then closing the tappel. So the average number of mat taps per day align well with the project design at 6 and 13 for furnace 1 and furnace 2 respectively, but the model then goes further to show the range of mat taps while considering process upsets and planned and unplanned downtimes, as seen with the lower taps, and when the owl operates optimally, as seen with the higher taps per day. You'll see the number of maximum taps per day that furnace 2 can achieve is at a high of 20. Very, very high, exceeding the current industry max at 14. So given the results of the model, we will then able to validate the design of the hatch furnace of 4 mat tappels with the aim of reducing tappel and launder wear. Then moving over to another crucial equipment unit, which is the and operations, which is the converter cycle. So we know that a converter goes through a series of activities to produce the final converter mat product. They include variable activities that are oil dependent, such as waiting for furnace mat or crane or ladle, and then independent activities such as when the converter is turned into stack and blowing. So the graph shown in front of you gives the percentage of time that the different activities take up of the cycle. Seeing the variability in activity durations for the same converter, as seen with the blowing times in blue over here, it allows us to understand how the converter activities are impacted by our operations, namely the 2-crane interaction, availability of furnace mat, and the impact of layup. So analyzing activity contributions to the overall cycle time was a gateway to interrogating the project design to either validate it or to identify bottlenecks. So while we did validate the design as shown before, the model did highlight some unexpected behavior in the system. What I've highlighted in red on the graph here is the silica addition duration. So this is an unexpected discovery, given that silica feeding happens during the blowing process. Hence, the fact that this shows as a durations on its own means that silica exceeded the blowing time. So through investigations of the results, we found that there was a design flaw in a common converted flux and reverts feeding system to the new converters, where only one material type and one converter could be fed at a time. So this meant that when you had both new converters operating at the same time and both blowing, one has to wait for the other to complete the feeding process, which causes silica feeding to exceed the blowing time. So the results prompted the team to redesign this 2-feeding system before project implementation, thereby improving our throughput by 2%. So Zimplats also requested additional flexibility in the plant design to accommodate catch-up capacity in cases of extended furnace downtime. So the catch-up capacity was incorporated in the new furnace design, and then the model was also employed to determine if this could be achieved from a logistical perspective. So the 2 graphs show the impact of increasing the concentrate feed rate from nominal rate for furnace 1 and furnace 2 on the annual concentrate throughput and the converter cycle times. So you'll notice the graphs reaching a plateau at around 30% increase in nominal feed rate. So even though the furnace has capacity to process higher feed rates, the converters downstream have optimized their cycle durations and hence do not have the same capacity to keep up with the furnaces. Hence, an additional converter would be required to meet throughput targets during the catch-up period. Then another valuable exercise was the capital optimization. So we identified 3 optimization opportunities and wanted to review into our operations and impact on throughput should those opportunities be realized. So the first was, is the removal of the converter slag granulation facility and incorporation of the hot slag return operation that is currently existing at Zimplats. And then the second is deferring to debottleneck the mat granulation facility to upgrading equipment and increasing capacity. So essentially operating the expanded oil with the existing mat granulation facility as is. And then third is to use the existing 12-ton ladle fleet at Zimplats for the full expansion. So the graph in front of you shows the concentrate throughput achieved for the various capital optimization scenarios and different hour operating configurations. for furnace 2 coupled with either 2 large converters, 1 large and 1 small converter, and then 1 large converter only. So the scenario starts from full capital investment to realization of all capital optimization opportunities. What's clear is that if you run furnace 2 with 2 large converters, you'll meet a throughput target and realize one optimization opportunity, which is to remove the slag granulation facility. So in conclusion, the dynamic simulation was able to confirm key design parameters and validate the smelter expansion design. It highlighted a project design bottleneck, which could be remedied before implementation to improve our throughput by 2%. The model was also able to confirm that catch-up capacity could only be achieved with the addition of a third converter, and also confirmed that the new 21-ton ladle fleet and debottlenecking of the converter matte granulation facility must be implemented to meet throughput targets. So by considering a system in its totality and not as isolated subsystems, the simulation approach yields optimal solutions that meet overall system objectives. Simulation by far is the preferred tool for evaluating complex and large-scale systems due to its practicality in representing reality and its power to quickly evaluate what-if scenarios. It is a powerful tool which, when used properly, can provide the insight necessary to prevent both poor system designs and operations and to produce productive and efficient ones that maximize throughput and production. Thank you very much. That's all from my side.
Yeah, thank you so much. Very informative and very much linked to operational readiness when it comes to projects, to make sure that there's no hidden surprises. You do not want to start up a furnace and tap and then find out that, oh my goodness, your oil movement is not good enough, and you sit with a problem. You want to know that in advance. Thank you so much, Tasneem. Do we have any questions online? Let me just quickly have a look here. I don't see any. Any questions for Tasneem from anyone? I don't see any on chat or questions and answers, and I also don't see any hands. So your presentation was quite crystal clear, I suppose, Tasneem, and the Zimplats team, I know they're very happy with the work that you've done and implementing definitely some of those outcomes already. There's one question from Louis from Zimplats, and he is asking, explain the third converter, question mark.
In what context exactly?
Yeah, maybe Louis, I think you can still speak, so maybe you can come in there.
Yeah, I was asking, you said there's no catch-up capacity without third converter. Are you talking about a third converter over and above the 2 large converters which you have put in, or what? What exactly are you referring to as third converter?
So essentially, with the 2 large converters and the furnace operating at its throughput capacity, we will increase our throughput through the aisle during that time, but we're not going to reach that throughput target specifically. So if you want to reach that target, we'll need an additional converter. Because as I've showed before, the furnace design does allow for that additional catch-up capacity, but given our logistical constraints, and given that you cannot really much optimize cycle durations, the constraint lies at the converters. So you'll need an additional one to reach the throughput targets. Yes, I hope that answers your question.
That makes sense.
Yeah.
Thank you, Louis. There's a question from Benny Havenga from Impala Smelter. Is the model's prediction based on historic data, activity, duration assumptions? How will an improvement in accuracy or assumptions change the simulation?
Okay, so yes, as I've mentioned before, we first have to develop a base case. So looking at the existing operations, and we need to feed it with the operating philosophy. We need to feed it with operating data. So then it's basically an iterative process, because before we can use the model as a tool to make decisions, we need to know that it can reflect existing operations. So we'll feed it with historic data. And as well, it's an iterative process. We need to engage with operations. Is this what we are showing you from the model? Is this what you see on the ground? So once we've validated that, we also look at certain modeling assumptions, because you can't model every single scenario that happens on site. So with some things, you need to just make an assumption for how certain things would work. But yes, we need to answer your question. Definitely, once you get the results of the model, you have the discussion, the workshop with the operations team, and you see certain results, we could maybe look at different modeling assumptions and look at the different outcomes of that. And that can also form part of the what-if experimentation scenario analysis that I mentioned before, where you can look at different operating philosophies and scenarios and see the impact on throughput operations, on throughput and production efficiency. Yeah.
Thank you for that one, Tasneem. That brings us to the end of this presentation and this the question and answer session. So if there's any more questions, please don't hesitate, just type. Tasneem will answer as we move along, or we can always reply via email as well. But please continue with that. Thank you again, Tasneem. It was a pleasure having you.
Thank you so much.
All right. Then next on our list of presentations, and I must just bring this to your attention, that our third presenter has a logistical problem and asked that we just swap him with the next presenter so that he presents last in the session. So we will jump to De Nova's presentation and go then to the on the program 10:10 presentation. Dealing with metallurgical engineering education, how do we sustain and grow our talent pool? And this will be presented by Peter Heys. And this is also, is this a live presentation, Camilla, or is this online? Or is
It's a recorded presentation.
This is a recorded presentation. So if there's any questions on this, then please, we need to type, and Peter committed that he will answer any questions. Just a short resume. Peter is a professor at the University of Queensland and has over 400 research publications in international journals and conferences. Peter has over 45 years experience of teaching in extractive metallurgy. Prof. Heys' research encompasses experimental studies on high-temperature phase equilibria, reaction kinetics, and mechanisms in high-temperature metallurgical systems. He was the foundation director of Pyro Innovation Center at the University of Queensland. A feature of research has been focused on fundamental science in support of industrial process and process development. Good. So yeah, we will listen to the recording and then have questions on that after the recording. So yeah, thank you, Camilla. We can play the presentation then.
Hello everyone. I'd like to start by thanking the organising committee for this invitation to speak at the conference. It's great to see pyrometallurgists coming together to share knowledge and experiences. My apologies for not attending in person. I'm not undertaking international travel at the present time. The issues of finding and retaining metallurgical engineers once again attracting attention of management as global demand for minerals and metal products increases. Some of the topics I'd like to discuss in the presentation are listed on the slide. First, some introduction, some background to what we're trying to achieve here. Then some discussion on what attracts students to the professions and careers and programs. How do we maximize awareness and attraction to our discipline? How can we help high schools in making them aware of metallurgical engineering? And for university programs, how do we structure them so it's easy for engineers and scientists to study metallurgical curriculum. This industry's role in developing a metallurgy workforce for the future, I think, is critically important, and is the main thrust of where I think future initiatives should be taken. Concerns about the decline in enrolments in geosciences and mining and mineral processing are not new. The Minerals Council of Australia in 1998, in their report Back from the Brink, identified a shortage of metallurgists, mining engineers and geoscientists in Australia. And the International Mineral Processing Congress, IMPC, has issued a number of reports on this issue over the years. Some of the points I'm going to make have been acted on largely by individuals and by selected organisations, but there's no coherent strategy across the sector. And in my view, the fact that the problem still exists is not, there's no solution, rather that the appropriate actions have not been implemented. Now, we know the governments around the world have invested significantly in education over recent decades, and the proportion of people who have completed tertiary education is now higher than it's ever been. But the proportion of students taking STEM courses still remains relatively low, particularly in African countries. So the sources of trained metallurgists have declined in the UK, Europe and the USA as these countries have moved away from primary processing of ores, minerals, and universities have realigned their programs towards downstream processing, advanced materials and manufacturing. So the onus is now on individual countries to provide the educational needs for their local workforces. I believe our efforts should be targeted towards these objectives: providing the minerals and metallurgical industry with professionals with knowledge of competency in science, technology, engineering and mathematics, that's the STEM fundamentals, specialist knowledge and skills in process and metallurgical engineering, and the ability to work productively and professionally in engineering practice. So I think these are the core targets that we should be aiming for. Since new technologies will be required to address challenges faced in the coming decades, we're going to need smart scientists and engineers who drive innovation and the implementation of these new technologies. So this will require, in my view, deep learning and competency. And to do this, we need to support practice in application, in problem solving, and provide time to absorb and understand new concepts. So short courses will only be useful in the long term for knowledge transfer. They don't really build competency and skills. So, in my view, again, the development of these attributes in individuals requires creating opportunities for those individuals, providing support at all stages, and this takes time, effort, and a range of activities and practical experiences. So it needs some strategic thinking about how we go about this and integration of those steps. Now, many surveys have been undertaken by our universities to identify the factors influencing the choice of discipline at university entry level. Most of these studies have been carried out in OECD countries. these results don't necessarily translate directly to the situation in South Africa. I found a recent survey by Abe and Shikoko of STEM students in South African university. And they identified 3 key factors that influence these students' career decisions. That is interpersonal factors, that is influenced principally from their families and high school teachers. This is fairly obvious and probably common to most tertiary students, since students spend a long time with their families and at school. So it should be no surprise that these interpersonal factors are important. Intrapersonal factors are really the student's own opinion and judgment. These are STEM students. They're motivated, and half these students identified their passions, dreams, aspirations and desire and curiosity to study a career to be important in decision making. So these are top students who actually want to change the world, and we should be feeding in with that desire when we offer opportunities to students. The third one is career outcomes expectancy, and clearly financial issues are front and foremost, as well as the long-term career, job and opportunities. So most students perceive a career in STEM as economically rewarding. This is great for metallurgical engineering because metallurgical engineers are relatively well paid, and so we should be competitive in that last aspect. But it's up to the industry to explain the opportunities to those students at an early stage. So, but looking at the results of this survey and similar results from OECD, a notable feature from my point of view was that almost completely absent is the influence of potential employees in respective industry sectors. So we used to, many years ago, undertake our education on the plant, on the job learning. With the advent of the tertiary education sector, we've actually split off the learning to a large extent between industry, productivity, and what we do at universities. So I think that industry is leaving the job of education to universities, and what's happening over time is that gulf is getting bigger, and then the opportunity for attracting people is getting less. So students at high school at universities are largely unaware of the importance of metals in a wide range of opportunities available to them. So to raise the profile, a positive, forward-looking view of the discipline is required. And we need to present the profession as an attractive career path to undergraduates. We need to change this negative view that the general public holds about the minerals industry, stemming really from historical practices, environmental and employment practices. So COP28, the climate emergency and the need for critical minerals to support this energy transition offers us a rare opportunity to change the narrative and to get students to look at these opportunities, to see how all these different metals contribute to green technologies, solar power, renewable energy, electric vehicles. These are the sorts of things that we should be telling them about at high school and universities. So, knowing that students are strongly influenced by teachers and experience at high school, and they're idealistic and self-motivated, there are opportunities for us to do more to help teachers and students at high school to understand the importance of metallurgy in our society, and to further encourage STEM students to go to the next level. I came across this paper by Roerich, which suggests an approach to teaching chemistry involving the following: focus on real-world problems, centrality of engineering, context integration, content integration, STEM practices, making sure that students have 21st century skills, and informing the students about STEM careers. It seemed to me that this structure summed up the sorts of things that we're looking for. They may not be in the normal high school practice, but it's something that we could possibly take to high schools and say, can we help to bring these to you and help with you in delivering these to the students? In terms of STEM practices, Roerich actually found out that designing things, which is part of the STEM practices curriculum, in the general, boys and men focus on designing things such as cars and rockets and built structures. And this focus on building things and designing things tend to have a negative impact for girls who are motivated by more touchy-feely type things and wanting to help the community and change the world. So I think this is something, again, that we need to take notice of. We need to try and find examples of where we can do STEM practices which will attract a greater number of women and we could include health and environment, recovery and recycling of metals, and give them more an opportunity to study those. So following these guidelines, industry and the metallurgy academics can support these kind of initiatives by providing project topics for high school teachers and students, supplying equipment that enables simple experiments to be undertaken, and providing the teachers with examples and explanations of metals processing that be incorporated into the learning. So we have to educate teachers as well as students, and teachers, like engineers, are very busy people, and so we have to do some homework for them to help them out. For example, we should be providing them with things like coloured particles of different densities, which we use in mineral processing research to enable the separation, or to see how we can separate particles on the basis of density. Ion exchange resins to assist in water treatment, for example. Again, showing how we can clean up the environment, make it safe for everybody. Optical microscopes, I think, is a good idea, and polish samples of different materials, metals and minerals. This encourages students to explore the microscopic world they're largely unaware of, and it's something that will stimulate their curiosity. It's a bit like deep sea diving. There's a different world down there, and anything that can stimulate that curiosity is to be encouraged. One of the things that important about university is the structure and content. flexible entry, program content, and university program structures are important in encouraging students to come study metallurgy. So in some universities, not all, but in many instances, the students enrolling in universities in the first time are required to select a department, a school or area of specialisation at the point of entry. So this direct entry mechanism is an inherent disadvantage to the recruitment of metallurgical engineers. So expecting students to enter metallurgy when they don't know what it's about is a tall ask, and you can't expect them to choose a career they don't know anything about. So university administration should be encouraged to allow flexibility and allow students to transfer programs during the first 2 years until the start of years 3 and 4. My experience over the years is most students entering first year engineering don't know which discipline to do. And they're flexible. They can be persuaded if you catch them early. Once they're locked in, then you've got no chance. So years 1 and 2, it should be the focus of attracting these students. In terms of program content, I'm not going to say a lot about this because the IMPC has done a lot of work on with industry on identifying the key competencies and specialist knowledge that metallurgical engineers should know and should be competent in and are sought by industry. And this roadmap, the reference to which is given in the proceedings, can be used to help education providers and employers and young professionals with their career. University program structures. Clearly, the offerings will differ across countries and regions, reflecting local industry needs. But the number of universities that offer 4-year metallurgical engineering degree programs have gradually decreased, especially in OECD countries. And the availability of programs across countries varies also considerably. So where metallurgical engineering degree programs can't be offered for economic reasons, then we need to look at other alternatives. So specialist metallurgy courses can be provided as sub-programs or majors to be taken in 3rd and 4th year in other engineering programs. So these specialist metallurgy courses should build on the sound fundamentals and understanding of principles and practices relevant to the industry as outlined in the IMPC roadmap. We know that technologies are going to change with time, and we need people who can adapt to these changes. So it's necessary to develop people who can innovate and problem-solving skills. Very briefly, here's an example of the program structure that we offer at the University of Queensland. This is actually now part of the degree in chemical engineering with a major in metallurgical engineering. And the colour code here tells you the split between mainstream chemical engineering and metallurgical engineering major. The green program is what chemical engineers do as part of their chemical engineering major. And within that, there are courses which all metallurgical engineers need to know anyway. Chemical thermodynamics, fluid dynamics, heat and mass transfer, reaction engineering. These are clearly things that all metallurgical engineers should know. But the specialist courses are listed in the brown part of the diagram here. So an introductory course of metal production and recycling to give the students in the second year an overview about the scope of metallurgical engineering, the range of activities, and how the importance of integration between the various steps, before we go on to looking in detail at the likes of process mineralogy and comminution, physical separation processes, pyrometallurgy and hydrometallurgy and electrometallurgy, and finally the opportunity to do thesis work and specialist studies. So this is how we can put it together with kindred professional programs and still come out with the attributes that we're seeking for those engineers. As I said, establishing contact with industry, I think, is most important. And again, from experience, talking to students who've been through our programs, quality work experiences and providing vocation work in first and second year to engineering students is the key to getting more students through the door. And preferably those first and second year engineering students should take part in projects with third and fourth year students working in industry under the supervision of an engineer. This way they build up the teamwork, capability and understanding, as well as learning from other members of the team. So I think this is a great way of getting students involved early on. As I say, first and second year is when you can make the switch. It's when you can attract people and demonstrate that metallurgical engineering is a hands-on discipline and it's exciting and rewarding and different. You do different things every day. It's not routine following codes. The other thing that industry can do is offer part-time work, paid part-time work. If the universities are not near an operating plant, metallurgical plant, then there's sure to be head offices in town. And there's a chance for experience and internships with professional engineers who are working on design and long-term development within the company. And students can then see what the future is in for them. So this is something they can do when they're not doing their lectures and practicals and other formal teaching. So there are always gaps in the curriculum to do this part-time work. And this helps to support the students financially and gives them extra incentive to being involved. These, I think, are the key steps which could attract students into our profession. And over the years, industry, particularly in Australia, has cut down on these important initiatives. This is where we have to change direction and get contact with the students. Personal contact makes the difference. Sending out flyers on the web and those sorts of things, they're great, but personal contact makes the difference. In addition to that, facilitating student visits to operating plants to observe operating practice firsthand is really important to show students and to supplement their learning during lectures and tutorials, so they understand how all of that theory relates to practice. Industry can provide financial support through fee and living scholarships to students as well to take up studies in the discipline. This is something that you can use to differentiate our discipline from the other disciplines, where there is plenty of students looking for the standard engineering, IT, civil engineering, mechanical engineering. Here here you can target the students. Because we're talking about a smaller number of students, there's an opportunity to, I think, support fee and living scholarships. I know it's hard right now because the metal prices have gone down temporarily, but the industry, if it plans to be there for 20 years, it should be investing in that 20-year program. It should be looking forward to the future and showing students that they expect them, those industries, to be there in the future for them to build their careers. This can be reinforced by engineers making presentations to student societies at the universities and talking informally at activities. And this leads on also to engagement in mentoring schemes with undergraduate students. Key messages then to industry: demonstrate the latest developments in technology and industrial practice. Explain the opportunities for future innovations and improvements. This is what students want to see. Don't do what happened to me. I went to Sheffield in 1969. This is what I saw: a hot rolling steel rod through 4 stands, hand threaded by 8 men, no safety equipment apart from steel cap boots, using inefficient, outdated technology. This is definitely what I didn't want to see, and not what an inspiring metallurgical engineering students want to see. To be honest, it made up my mind that I wasn't going to be a metallurgist in UK. And I came to Australia because of the impression, that first impression I got at seeing operating practice in that site. I asked them when they put this rolling mill in. They said before the First World War. And it immediately hit me that these guys were not investing in the future, and there wasn't going to be a future for me in the steel industry in the UK. And I was right. So, young people are looking for stimulating, personally rewarding, greener and environmentally cleaner, sustainable futures. So if the metallurgical industry is serious about attracting smart people and inventive people, it needs to actively engage with them personally, stimulating their interest and supporting their development. So in conclusion, the minerals industry is facing shortages of students and professionals. It can no longer rely on expatriate workers, people from different parts of the country, world, to come in and fill in those roles. It has to be looking after itself. And in my view, the onus is now on industry to solve the skills shortage. We have to actively re-engage with students at high schools and universities, get face-to-face with those people, and demonstrate to them there's reliable, rewarding careers in metallurgical engineering, one that meets their personal goals and expectations. So we have to frame the messages to fit those personal views. Further details about the points I've made can be found in the proceedings, and if you want to contact me personally, there's my email address, p.hayes@uq.edu.au, and a website where students can download a free introductory text for metallurgical engineering. Thanks for listening, and I hope to stimulate some debate and actions with your respective organisations. Thanks again, and look forward to hearing more from you.
Thank you, Peter. And if we have any questions, please, you guys can type, and we will get it to Peter. It just again shows us the importance of making our own discipline attractive. We need to think of tomorrow. This is our responsibility today. The youngsters of today want to go into banking and IT. That is the 2 things. We need to make it attractive for them, and we need to play a physical role in doing that. So on that note, we are running a bit behind the program. We have one final session or presentation before we go on a break. I can maybe just ask Camilla, our next presenter, has he arrived?
It's also recording, Adele.
All right, so we can just go ahead with the recording. And this is then, let me just then see it. This is now the Nova's dry slag granulation process. That will be presented by Enzo Chiarulo. And I will just read his resume to you.
Sorry, Adele.
Adele, it's not that one, it's the next one. Sokran. So Enzo will probably will be the last presentation.
All right. So he will slot into the last presentation. Okay. All right. So maybe this is a good time for us then to take a break, I suppose, because it is 10:30, and then we will go and we will follow the program as per what we received. Just knowing that the last presentation will then slot in at the end. Right, Camilla?
Yes, correct. Just before the tailing session starts.
Just before the tailing session starts then.
Yeah.
All right, so let's do that then. So I'm going to ask that we shorten the break because we are running a bit behind, basically one whole presentation behind. And we then, this now 10:30, we allow our normal 15 minutes for a bathroom break and maybe a cup of coffee or tea. And then we can I then ask that we continue again at 10:45. 10:45, and then it's the 15 minutes, and we will then do the two presentations on Pyro before we then continue with the tailings. Everyone happy with that? The next session will be chaired by our own Wouter Broodryk. And I must maybe just thank Wouter for, he was the man behind this conference. He organized the conference with all the presentations. So from my side, Wouter, thank you. You will be the next chairman for the next session then. Perfect. Thank you, guys. And we'll see you in 15 minutes. Thank you.
We'll start with the second half of this reconference. So we have then 3 pyrometallurgical presentations before we start with the tailings presentations after that. So I'm going to introduce the next speaker. It's Rivashan Sakaran. He's the analysis specialist, having worked in the platinum smelting production space as a metallurgist and in the process control space as a control engineer. He's passionate about technology and the implementation thereof to improve efficiency and enhance automation. So he's going to speak. His presentation title is The Implementation of Automated Power BI Reporting at the Anglo-American Platinum Smelting Operations.
Good day, everybody. My name is Rivashan Sakaran, and I will be taking you through today on the automated Power BI reporting that was done at the Anglo-American Platinum smelters. My co-authors are Angelique Sazek, Danielle Kutsia, Winnie Mbiza, Tafazwa Ndlovu, and Natasha Van Blood. So taking you through today, I would like to take you through the context and the history of reporting at the operations, how Power BI was implemented in Anglo-American Platinum, the method of implementation that was used, the subsequent training and upskilling that was needed to be done and the challenges faced, and some of the case studies that were done at the various smelters and some of the conclusions and work that is to be done in the future. So technology is moving at a breakneck pace. With the advent of big data, machine learning, and artificial intelligence, there's continuous transfer of information that's needed, and this information should be leveraged to make decisions. The Anglo-American operating model helped lay the foundation for this to occur. And the focus of the technology that we're looking at now in general is the movement from a people dependency to a system dependency in order to make sure that there's a common understanding in what precipitates production. Thus, I would like you to take you through the Power BI tool today. And a point to note is that this deals with Anglo-Americans' values of innovation, and the implementation thereof would be able to show how we could ultimately improve the lives of people through innovation and the lives of employees. The purpose of developing this report is to provide critical insights into the health of the business, the health of the operations, and to provide management with pieces of information and with a detailed and compelling view. And as a result, compiling this will also ensure that there is a greater data integrity of this and a better way to produce and report key performance indices. So in the context of the smelting operations, Anglo-American Platinum operates group smelting in the middle of its value chain prior to refining and post concentrating. Concentrate is sent to the smelters. There are 5 primary electrical furnaces, 2 converters, and 1 slag cleaning furnace located in the Waterval smelter as well. All of these furnaces have a similar structure in terms of Power BI reporting as we're going to show forward. And in addition, a significant amount of reporting has been done on the auxiliary equipment other than the furnaces, such as flash drives, compressors, feeding systems, etc., to be able to ensure that this not only affects the furnaces, but across all pieces of equipment across the entire site. So historically, data used to be collected in data log sheets, if we could remember way back into the past, and this was manually used to create graphs and trends and analytics and decisions were made based on these manual captured pieces of data. This was then subsequently moved to Microsoft Excel, where the graphs and the automation of the information that was collected thereof was moved to Microsoft Excel. And I'm sure that almost every single company went through that journey. All of the problem-solving, monitoring, and reporting was thus done from Microsoft Excel. In the recent past, however, with the improvement in instrumentation and instruments and data storage and technology, there was the development of historians, and this allowed for more consistent measurement of data, such as the use of thermocouples, such as the use of pressure transmitters, and this allowed us to measure data at a higher frequency than before, which was rather ad hoc. This data frequency, however, was then stored into a historian, or the data at its frequency rather was stored into a historian, and this still required manual downloads into Excel. Some automation was still done, where the automation of the development of graphs, for example, into Excel was still done. And then there was the roll-ups of these pieces of information into specific tags, for example, to look at a daily and a weekly and a monthly tag. And in addition, we had SQL Server reporting services, which allowed us to generate tables of reports of key pieces of information. However, the company decided to take this a bit further and to develop actual reporting that tells a compelling story. And this was the Anglo-American decided on the use of Power BI as this tool. So what makes this tool powerful is that it can connect directly to these databases or historians and generate automated reports already in the structure, the format, and consistency that's needed in order to make decisions fairly quickly and fairly effectively. Now, the implementation thereof is a very, very key part of making sure that we are able to turn over the development of reports quite quickly. Initially, this was done through an ad hoc process where a site would come to us and then ask us to develop a report, and we would go through the challenges of developing that singular report. As a result, what was noticed is that a needed procedure was needed to be able to get to getting these reports out more consistently and more standardly in a more standardized manner across all of the operations as well. So firstly, an action plan was developed in terms of the reporting action plan to make sure that a strategy was developed of the types of reports that to be developed that were needed. The KPIs in each of these reports were defined, and with initial specific data frequencies, it's key to understand that this is the most critical aspect of the development of reporting, to be able to plan effectively so that we are able to then subsequently develop all the necessary queries, all the necessary visuals, and all the necessary resources that are needed to create these reports. Once the reports are structured and confirmed, then this moves on to the data validation stage, where we need to make sure that the data is actually being captured as we want it to. Once it's captured as we want it to within the historians, we then develop queries to extract that data from the historians into Power BI. Once in Power BI, these queries are then edited, and the Power BI tool is utilized to develop the visuals that are needed for the report. Once the visuals are developed, this then goes back to two different levels of testing, where the developer then tests it and then passes it on to the requester, who then does subsequent user acceptance testing to validate and approve the project. And the key point to prove, though, is that in order for Power BI to be utilized, it still needs to be utilized by people. And this could be an opportunity to be able to ensure that operational efficiency is improved by freeing up the time of the necessary people and their resources for them to focus on the analytics of the tool, so they make data-driven decisions rather than or analytics of the data rather, not analytics of the tool, so that they're able to make decisions, so that they do not spend too much of time collecting the data, but rather time analyzing the data. So in order to do this, we would need to understand the data health of the organization. What are the skills of the current set of employees? And currently we develop that through a talent assessment. We understand the key different roles that are needed in the organization and what are the digital requirements for each of those roles. And we develop a matrix thereof to understand the digital health of the organization, and then subsequently develop trainings to be able to then fulfill the gaps of that occur within that matrix. For example, an in-person training for a group of people, there are also self-training opportunities such as on the Power BI tool itself and other online resources such as Udemy, YouTube, etc. Now, this is a key aspect in terms of the implementation challenges, because not all projects have some type of challenge. And as much as Power BI is an excellent tool, a lot of people would have some resistance to it. Some of the key challenges that we face as an organization include the level of maturity at each site. And when I mean the level of maturity, I mean the data maturity at each site. Each site is not on the same level in the implementation of the digitization framework. As a result, a singular smelter and another singular smelter cannot have a one-size-fits-all solution, and the solution needs to be tailored for that individual smelter's operations. And in addition to that, the timelines and the resourcing needs to be effectively allocated to make sure that the different levels of maturity are equalized at the end of the project. In addition, people will start to believe if there's an additional amount of training, that apathy, there's some type of apathy that's going to exist, that this is an addition to their job. We need to remove that apathy through making them understand that this is actually and effectively going to make their job easier. In doing so, we generally try to always implement low-hanging fruit at first, so people believe in the tool. So you would be able to automate and save the people time. And once they believe in the tool, then implement other things which require a high amount of difficulty and a large amount of training. In addition, Power BI resources are scarce, and they are scarce skilled. So there is a lot of time and training that's required in order to train the necessary employees on the Power BI tool. But in addition, the development of that can take some time if there is not sufficient resourcing available, not just for the development, but for the maintenance of the reports as well. Now, looking at some of the implementation results of Power BI, we've developed since May 2019 to November 2022, for example, an increase of 192 reports. This allowed for an increase in engagement and this shows an increase in engagement in the reports, with the number of viewers increasing by 395, which is over 1,000%, and the number of views increasing by 72,000, which is over 5,000%. We noticed a slowdown on the number of reports generated, but there's a significant amount of reasons for that. We also developed subscriptions, so the number of views doesn't get added to the number of subscriptions or views through subscriptions doesn't get added through the total number of views. And in addition to that, a significant amount of time for a single developer is now spent when there are a larger amount of reports on the maintenance of the reporting rather than just the creation of reports. So there is some level of reporting which can be solved rather by additional development. And in addition, there has been some reports which have been combined or deleted after times, which resulted in a lower amount of reports and a lower amount of views. So let's look at some of the case studies that have been implemented. So an example of the case study implemented at the Mortimer smelter is the measurement of key performance indices at the furnaces themselves. We were able to use different types of reports for different key aspects of the furnace or the smelter in total, such as electrode management, for flash drives, for water management, and for binding. As a result, this allowed it to be used in different types of functions for shift work, for daily analysis, for technical reporting, and for problem solving. This is updated on a daily, on a shiftly basis, so anybody can access this from any specific time within the plant as well. And the reports that were used in the Mortimer smelter were then subsequently also used for ad hoc requirements, such as when the rebuilds were happening and they needed to monitor the ramp down and ramp up of the furnaces. These reports came in handy. Within the waterfall smelter, a similar type of setup was faced, where the technical team keenly noted that there is a limited collation of data occurring in individual metallurgist laptops, for example, which took significant preparation time, and it wasn't standardized, and they all had to create reports that were not consistent because everybody was doing something different on each of their laptops. And as a result, all of the reports were subsequently combined, and the outcomes thereof was a more consistent and straightforward setup of all of the reporting. As you can see from the navigation page, you can see a number of reports were set up, and anybody can access these reports in the technical team to be able to look at it on a consistent basis. And we were able to then take these reports for analytics, but also take it for reporting as well. This has resulted in significant time savings, which would take half the amount of time to compile a month-end report, for example. And again, its focus is shifting from the compilation of reporting and the gathering of data to the analysis of data. In terms of the Polokwane smelter, this was the first smelter, for example, to look into the setting up of an overall production report. And the basis of this was used then subsequently for the rest of the smelters, where daily and shiftly production report were usually collected on the SSRS reports manually and then shared via a communication method from the process overseers to the management on a daily basis in the morning. And this generally took between 30 and 45 minutes in the morning, especially during handover, which is a stressful period nonetheless. As a result of developing this report, this improved the handling of the data from 30 minutes to approximately 5 minutes. It minimized the mistakes and typing errors as a result. And this estimated reallocation of focusing on the plant during the shift handover period is estimated to be about 180 man-hours a year. And this also is important because it also measures the points at exact timing with history, with ease of access from management level as well to the control room level. In terms of ACP, another key aspect is looking at how we can look at contractual agreements. So we contractually utilize tankers from transporting material from mats from the individual primary smelters to the from the primary smelters to the ACP converters. And the availability of feedstocks and the way in which it's transported is a key measurement to understand how that will affect ACP's availability. You have to have stocks in order to make sure that your converter is running consistently and as stable as possible. And this in turn affects the outputs of the smelters themselves. As a result of implementing this data no longer in Excel spreadsheets, which can be tedious and susceptible to errors, this has allowed for higher visibility and quick identification of key problem areas in specific areas, so that would allow for ease of access for information for all the parties, from the contractors to the management level, to make decisions very quickly, to be able to turn this around very quickly, so that we are able to provide ACP with sufficient material consistently. In addition to looking at moving from a technical space and a production space, which was already very familiar with reporting in general, to now an engineering and maintenance space, Power BI has been used as the catalyst to be able to drive the culture of data-driven decision making. And previously, maintenance used to be always dependent on the experience of the relevant personnel, and there was an underrepresentation of reporting in general. And now, through the use of Smartsheet and Power BI, new solutions have presented themselves, and it allowed for the prediction of failures as well. And it allowed for more downtime analysis, and then allowed for alignment in terms of production and maintenance schedules. And it was also utilized in the human resource space to track training matrices to reduce the amount of time and administration that's required on the foreman, so that they would be able to get reports on their training, and the HR would be able to get reports on the training and training licenses and expiries, so that they would be able to be on top of this all the time. So where to from here? In addition to all of the work that's being done, we are also looking at applying deeper analytics, applying deployment pipelines, moving from development, testing, and production workspaces, looking at more data connection and shaping possibilities and growth into the future, and then looking at streaming into Power BI using direct queries and using cloud-based services rather than using historians. In addition, looking at the capability of putting in segmentation and cohort analysis alongside machine learning and artificial intelligence to utilize the metadata that we have to thus start making decisions based on other categories and other factors that could have influenced why the data is behaving the way that it is. Thank you so much. I appreciate it. I appreciate you listening to this, and I hope that this inspires you to move along in your data digitalization journey as well.
I'll say thank you. Yes, I believe that was inspiring. So we'll move on to the next one. That was a recording. So the questions, please type them in the answers question pane or in the chat. See, there's something in the chat, so we will send that per email onto Rivashan and then get the answers back to you. So the next presentation is also by him, so like they don't have to read the CV again, and that is on the impact of feed composition on the recovery of base metals in an electric furnace.
Good day, everyone. Again, my name is Ravashan Sakran, and I will be taking you through today my next presentation, which is the impact of feed composition on the recovery of base metals in a PGM electric furnace. My co-authors are Prof. J.D. Leroux and Prof. Andri Garber-Craig, and this work was done in collaboration with the University of Pretoria, based on my master's in engineering for metallurgical engineering. So taking you through a quick content of this presentation, we're going to look at the context and the purpose of this work, a quick process description and theory of smelting and how the smelting occurs, some information on how the samples were collected, and where they were collected from, and where the data was collected from, and some information about the results, looking at a recovery model, upgrade ratio model, and mat fall, and some concluding remarks. So why is recovery important? Effectively, because ultimately high recoveries are indicative of processes that are more economically viable and allow for a greater reduction of waste. And the more effective a process becomes, the more greater the valuable material is located within the product. And mining companies need to understand recovery in a better way in order to enhance their portfolios. And there are various factors that affect recovery, including but not limited to the mineralogy of the feed, the process flow, the operating variables, and the concentration of the variables within the feed. And that's currently what we're looking at today. So a quick process description as well discussing this is that the smelting operations for PGM industry operate on a very similar basic mechanism where the ore from the mines is sent to concentrators, which generate a wet concentrate, which is then dried and fed to an electric furnace, forming a product of slag and a product of furnace mat. This furnace mat contains your valuable PGMs, which is then converted to remove a residual iron and then subsequently sent to base and precious metal refining, where it is purified into its individual base and precious metal. Now, in the context of Anglo-American Platinum, when the work that was done, we primarily looked at the three smelters, the Polokwane smelter, Mortimer smelter, and Unki smelter. What is key to note is the differences between these smelters. So all of these smelters operate in different megawatt ratings, with Polokwane the largest at 68 and Unki being the smallest at 8.5. It is also worth noting that Unki is circular, whereas the Polokwane and Mortimer smelters are rectangular shape. Also, the type of feed that they feed is very different, with a Polokwane smelter feeding primarily Platreef ore, Mortimer primarily UG2, and Unki primarily, not ore, rather concentrate, and Unki primarily feeding concentrate obtained from the Unki concentrator in the Great Dyke. And so why is this important to note? Due to the depletion of the Marinsky Reef that we've seen, that there has been an expansion into the eastern and western limbs, into the UG2 reefs, and into the Platreef and the Great Dykes. What we have noticed, though, is that there are significant mineralogical and chemical differences between these concentrate types, where Platreef having a higher base metal concentration and a lower PGM concentration, with UG2 having significantly higher PGM concentration but lower base metal concentration, and Great Dyke being very similar to Platreef with a very high base metal concentration. The way in which they exist as well could be in the form of base metal sulfides or tellurides and arsenides in the case of Platreef, and the subsequent metal oxides that are associated with it, such as silica, magnesia, etc. And all of these play a role in how the recovery in the furnaces occur in the formation of slag, as well as the amount of matte that's formed. So how does this occur in the smelter? Well, the blacktop layer, which occurs when the furnace, when the concentrate is fed to the top of the slag layer, it dissolves through different levels of dissolution, desulfurization, decomposition, and melting. And as a result, these then form in the silicate matrix or coalesce within the silicate matrix of the slag, and subsequently settle through density differences and coalesce and settles at the bottom of the furnace. There are some physical entrainment issues where this may occur, or where there's physically entrained matte droplets still in the furnace slag, and this can occur where there's large temperature gradients within the furnaces, or when the gas bubbles that are forming in with the reactions in the furnace lifting up the matte particles to the higher levels in the slag. So what we ultimately looked at in some theory is that there is a theory that was used to predict the recovery of the metals in the matte phase. And this was proven by Grimsey that the recovery of non-ferrous sulfide minerals from the concentrate to the matte phase decreases as you increase the amount of iron. And this is due to the oxidation of iron occurring, and then subsequently the oxidation of cobalt, nickel, and copper accordingly. And this was then subsequently theorized by Eric Grimsey, and this was used and will be referred to as the Grimsey model. In addition, there is some flux addition that occurs in the Unki smelter in terms of the addition of lime, and in the Polokwane and Mortimer smelters, the blending of the UG2 to the Platreef in order to control some of the properties, some of them being chromium, for example, chromium percentages, and others being making sure that there is sufficient lime, for example, in the slag. In terms of how the data was collected, ultimately the metal accounting data, which measures the inputs and the outputs of the smelters, were used, and this was done, and this is done on a monthly basis. And ultimately, how metal accounting samples work was that a site-wide mass balance was performed, and this was ultimately used to get the concentration data of all the concentrate entering the furnace and the concentration data of the slag that's removed from the furnaces and the concentration of the matte that's leaving. This is done on a monthly basis to prevent any variances in the smelting process. The calculations of the recoveries of the base metals are calculated by the two-product formula to calculate the recoveries, the upgrade ratios, the matte fall. And theoretically, the Grimsey model will utilize the information received from the metal accounting concentrate data to create a theoretical KME, and the KME value is then used to calculate the recovery. So in the calculation, it was in the calculation of the model, we ultimately noticed that the model moved according to an order model, and subsequently it was theorized that the data model should follow an n order model. And ultimately, to calculate the constants in the n order model, the regression analysis was completed, and to calculate the values of B, C, and D, for example. And this was then minimized through the use of sum squared error and data validation of through the use of the Kolmogorov-Smirnov test through the use of 193 data points. This was done over the period of 2019 to 2020. From the results, which we see is that looking at firstly on the theoretical models and the Grimsey model itself, it shows inherently that the base metal content in the concentrate is as the base metal content in the concentrate decreases, the higher the amount of iron that is reporting to the slag occurs. So that means the lower the recovery of iron as well as the base metal content in concentrate decreases. In addition, in the Grimsey model, it shows then through the calculation of the KME values that at low iron concentrations, for example, between 0 and 60% of iron reporting to the slag, when that occurs at those low iron reporting to the slag, rather than not the concentration, when there's low iron reporting to the slag, meaning lesser iron is oxidized, this means that the trend is followed quite well according to the theoretical Grimsey model. However, when greater iron is reporting to the slag, where that means that more and more of the iron sulfides are oxidized, we start to see a deviation from the predicted theoretical model. What's interesting is that the deviation is that the recoveries are actually higher than the inherent theoretical model as provided by Grimsby. So what we also noticed is that there is a relationship occurring in the concentrate between the iron content and the base metal content of the feed. As a result, we were able to then use the base metal content as a proxy for the iron content in the feed, utilizing this formula as well. In order to mitigate those differences, in order to understand those differences as to why we would see those at the lower iron concentrations, it was then thought to use that data-driven model, that regression analysis, to get a better idea of predicting recovery, since the theoretical model, especially at lower base metal concentrations, did not match the theoretical model. So a data-driven model was used, and it can be seen that the data-driven model, especially for base metals, is fairly fits the model very well, fits the data very well. And the same can be said for the upgrade ratios as well. This fits the data very well based on the data-driven model. So in addition to those data-driven models, the mat fall calculation was also shown, and that the Mortimer smelter, Polokwane smelter, and Unki smelter ultimately fall on the same line. What's interesting to note, though, is that the Unki smelter does have some variation, but this was due to some of the calculations that were done was assuming when the mat is calculated, the amount of mat that's calculated, it is assumed that there's a constant silica usage in the mat, silica content in the mat when it's poured into the silica sand beds. And in addition to this, there was an assumption that the lime that was added into the concentrate was always consistent and had a constant concentration the entire time. And the silica that's used for the mat tapping is also constant in concentration at all of the time. So how can we take this data that we get from the recoveries and ultimately apply it? So sustainably, how do we ensure that the sustainability of the company can be improved through the use of this type of model? Well, firstly, the amount of mat that can be predicted, along with its concentration the amount of mat that can be produced based on the composition of its concentrate, is an important factor to note. It will tell you how much of mat you can expect at smelter and inform metallurgists on day-to-day decision making. In other aspects of this, it can also help with the planning of the furnace, and it would be more aligned to how we would plan the shutdowns of the furnaces themselves. The maintenance profiles then can be adjusted more readily to understand which would be the best types of blends to make sure we have the highest availability, but not only the highest availability, but the highest throughput through the furnace. So an example of this is showing that Polokwane actually has the lowest amount of energy required for the amount of metals that's formed, based on the amount of metals in the concentrate. But at the lower end of the spectrum, and then this is at higher base metal concentrations, whereas at lower base metal concentrations, they are very similar to Unki and Mortimer. So Unki and Mortimer would probably be better to smelt material at lower base metal concentrations. Unki only smelts grade DAG, however, so that's a logistical issue on their side. And some concluding remarks is that to show that the concentrate itself plays a significant role in the manner of the formation of the mats and slag products and their properties, and ultimately drives recovery. The amount of base metals in your concentrate ultimately drives and is showing through a model that this is the primary driver of recovery. And as a result, the associated PGMs with the base metals themselves, through the different mineralogies of the PGMs associated with the base metals, should be also aligned with the recovery of the base metals. As a result, this greater understanding of the feed then allows us to lead to better planning in predicting the recovery, allows us for better planning in predicting the amount of material formed, and also allows us to develop operating strategies to run the furnace better, and allows us to look at possible energy savings when it comes to how we feed to the furnace and how we route the blends to the different furnaces. So if you have any questions for me, you can reach out to me on my email address, ravashan.sakaran@angloamerican.com, or you can contact me perhaps on my LinkedIn profile as well. Thank you so much. Appreciate your time.
So thank you. That was quite excellent, and I'm hoping it excited the pyrometallurgists among us. Yeah, so that's it. So please put your questions in the questions and answer box underneath, and we will send for both presentations so that you can respond to that. Okay, Camilla, I'm not seeing Enzo online yet. So shall we start with
either? Nazli, have you had any word back from Enzo?
No, Camilla, unfortunately, he hasn't come back to us.
Okay, I think, Wouter, let's then just continue.
Okay, so we're going to start with the tailings presentations then. So first up is GISTM topic 5. It's emergency response and long-term recovery, presented by Ilse Okamp. Short CV for Ilse. Ilse is an experienced facilitator, trainer, and lecturer, and presents modules on social impact assessment and public participation on several short and university courses. She's a co-author of the Social Impact Assessment. Ilse has managed and conducted several public participation processes and conducted more than 150 social impact assessments during the last 21 years. Her experience includes strategic assessments, social management, and monitoring plans, social due diligence, gender studies, human rights, mine closure, and social development initiatives. This will once again be a recording, so please put your questions in the Q&A pane, and we'll get them to them. Thank you.
Hello everyone, my name is Ilse Okamp, and I want to talk to you today about the GISTM topic 5 and how we implemented it. I work for a company called Equispectives Research and Consulting Services, and we've done this work in consultation with Knight Pisolt. And you might ask sort of like why we need to talk about GISTM, or you might even not know what GISTM is. So GISTM stands for the Global Industry Standard on Tailings Management. The International Council on Mining and Metals, ICMM, was established in 2001, and in 2020 they developed the GISTM as a response to mainly the big tailings failure in Brazil, which I'm sure you're all familiar with. And since then there's also been a number of other failures, and it's been with us for quite a while, and all the ICMM mines are supposed to implement the GISTM on their operations. So my focus today, I'm a social scientist, and is on GISTM and social performance. So the GISTM is organized around 6 topic areas, and there are 15 principles and 77 auditable requirements. And what I aim to do is to have an integrated approach to tailings and the management of tailings. And interestingly enough, social performance spans all 6 topic areas of the standard. There's just some stats for you, which I'm not going to read. You will see the topics are affected communities, integrated knowledge base, design, construction, operation and monitoring, management and governance, emergency preparedness and recovery, and public disclosure and access to information. Today we are going to speak about topic 5 specifically, the emergency preparedness and recovery, but you can see all the topics goes hand in hand. They overlap in some places, and in some incidents, as you say, but we've done this before, we're already doing this. So they are all holding hands. So just for those of you who are not that familiar with social performance, social performance refers to how a company handles its commitments, interactions, and activities, especially relating to local communities. And you know all what a big influence the communities around the mine have on the mine itself. So that is something that you always need to consider, and that is why the social people got involved in tailings management. But you can now imagine that this is a mammoth task, and there is a lot to be done, especially some mines have a lot of communities around them, especially mines in more urban areas or closer to urban areas. And then other mines are quite far away, so from any people, but they have big tailings facilities which might have a big implication when should it fail, and therefore we want to eat this elephant one bite at a time. So Impala's decided then that we will have a phased approach to the GISTM. So the first phase would be the desktop study, the second phase would be workshops, and a third phase would be implementation. So this approach requires unlikely friendships because we tend so much to work in silos everywhere in government, in life, and also in mines. So the engineering guys often don't know what the stakeholder engagement guys do, and then you need to also include health and safety, the processing plants, tailings, contractors, and human resources. So all these people play a role in establishing how to implement a safe emergency response plan and how to prepare for that emergency response in the case of a tailings failure. So in our first phase, we want to understand what needs to be done and who must be involved. So this is, in this phase, it's very basically a desktop phase with a few online meetings. It doesn't have any external stakeholders that participate in this phase. It's all within the mine. So you use desktop research to determine certain things, and the key stakeholders is usually we start with the tailings guys and the stakeholder engagement management leaders. And so we identify who our stakeholders are, and usually the stakeholder engagement guys know who are the outside stakeholders, but there's also inside stakeholders. So inside the mine, emergency response services, transport services, for instance, who will have to transport people, the control room, all these kind of stakeholders we identify with the team from the mine. And then we do a stakeholder analysis to see who must do what at which time. And from that, we developed a stakeholder engagement strategy on how will we engage each stakeholder group going forward. Also, part of this desktop research is to have a social impact assessment per breakage scenario. So what we do issue, those of you who are engineers and technical people know that there are different breakage scenarios and different flows of tailings. So we look at each of those and say, well, if it breaks this at this side, this will happening, and if it breaks there, we need to consider this as well. So, and then we developed social plans to address the gaps in the data that we've already gathered. The second phase, we had limited stakeholder engagement. So, and that also, we also had done some site visits and had workshops with people from the mine. So, first of all, we have introductory conversations with the service providers. That's your typical hospitals, ambulance services, the first responders, the disaster management people in the municipality, and so on. So we wanted to find out what's there already. And then we also drive through potentially affected communities. So we haven't spoken to the communities yet because we don't want to create panic. But we looked at how far are they from the tailings facility? What does their houses look like? Are there any sensitive receptors like hospitals, clinics, old age homes that we need to consider. And then we also had participatory workshops with internal staff, and some of the people looked at us a little bit strange because it was really participatory, and they had to do a bit of work and engage in groups. And what were the outcomes of this was that we had a better role clarification. So who does what and when, because everyone has a specific task and a role, and in a disaster situation, you must do that without even thinking. We also discussed about the risks of implementation. Some communities are more sensitive than others. In some communities, people will go and build their houses in the flow area just to make sure that they get resettled or whatever. Or these people are, the communities might not have a good relationship, or it might cause panic and protest and so on. But also maybe your mine does not have enough staff. You do not have any backup emergency equipment that you might need, like gloves or food parcels or whatever, or more technical things like the right kind of cars or vehicles. So then we also looked at a roadmap to the GISTM compliance. What can we do to make sure this mine can apply the best it can to GISTM? And we developed detailed consultation plans for the next phase of the project, so that we can be sure that who are we going to consult, how are we going to consult them, what are we going to tell them. And the last phase, when things are getting real, and we this is the phase we are currently in, you need to appoint a champion for each task, because people already have their own jobs. They don't want to do something extra or new, and now you bring this on top of that. So if you're not specifically going to appoint somebody to run with it, it's not going to happen. And then again, we look at how practical it is to implement the plans, and then we can adapt our strategy accordingly, because things change, the economy change, we have elections coming that might change things. There are all kind of changes that you do not have control over, and therefore you need to have adaptive management to continue changing as necessary. And here is where you start to, with your stakeholder consultation, and to start to implement the plans. And just as an example, we have different things in different mines. So people were saying, yes, maybe in our mine it will not work to speak to the ward councillors. You need to get somebody from the school to be involved, or we don't have telephones, the cell phone towers doesn't work. So what we want to do here is to send people with bikes or whatever. So you need to make sure it fits the environment that you're working. So we've learned that it's very important to involve the operational staff and all the relevant external stakeholders, because maybe some things are already in place, you don't know. And you don't want to redo work or do someone else's work, and so on. And also each operation is different. It's not a cookie cutter thing that we are dealing with here. It's not one size fits all. Your operation has unique circumstances and challenges, and therefore your plan will differ from the mine next door, or in another province or another country. And it's very important also to adapt to the needs of the operation. The plan needs to fit in as smoothly as possible with current operation. You do not want to reinvent the wheel. It's also important for the operation to buy in, because remember, there will not be any consultants when this happens in the area. It will be the people on the mine dealing with it. It will be the stakeholder engagement, people who will have to deal with the stakeholders and inform families of the issue, and the CEO would need to deal with the newspapers and. So if you don't buy in, no one is going to know what to do, and it is, in the end, it is your plan. But we also realize that extra human resources might be required to implement this successfully, and that is also a challenge. You know, there are cost cuts everywhere, the economy is not great, the prices of minerals go up and go down. So it's what this means is there's an element of long-term planning. Although we want to implement this as soon as possible, there is also the reality is that we need to plan in advance for this. Yes, and I just want to thank Impala Rustenburg, Zimplats and Marula. These are the mines we've worked with, and then Nightfield and the Impala corporate office that was also very instrumental in this whole project and gave us lots of guidance, ideas and challenges. And if you have any questions, you're welcome to contact me. My contact details are on the first screen. Have a great day.
Thank you, Ilse. Yeah, as you see, Impala is, well, Zimplats, everyone is highly invested, I suppose, and with the JSTM and committed to take that learnings to our tailings facilities. Okay, we're gonna veer off our program a little bit again. So Enzo Chiarulo has come online after his after not being available earlier, and we appreciate you being here. So we'll do the presentation of earlier. So the title of that is the Nova's dry slag granulation process, the experience on EAF and LF slag in the steel industry. Just gonna read you a short CV as introduction. So Enzo is the head of environmental technology at the Nova. He has more than 10 years experience in engineering roles with significant experience in the industrial environment. He's involved in the increasing impact of the circular economy in the steel industry by the byproduct valorization and the exploitation of waste heat. Enzo, thank you for joining us. For those that have just dialed in for the tailings part, here's a free pyrometallurgical presentation, and let's learn from each other. Thank you. When you're ready.
Hi, Enzo. Enzo, can you hear us? If you're trying to talk, you're on mute, Enzo.
Okay, he might not be in front of his computer, so we'll change the program again.
Okay, do you want to, sorry about that. Do you want us to do the next one, Wouter?
I think so. Okay. So next presentation, back to tailings, is the SANS 10286 update by Andrew Copeland. Just a quick introduction of Andrew Copeland. He's the technical director at Nightfield. Andrew has had extensive exposure to the international mining industry and to the full chain of mining activities and project stages for over 35 years. Andrew is a technical specialist in the area of mineral residue management, including filtered, paste, and thickened tailings, with a master's degree in mine backfill. He's an engineer of record on a number of large tailings facilities in Southern Africa. So thank you. That is going to be once again going to be a recording, so questions will be emailed to him afterwards.
Never get tired of looking at this slide and watching this video of the tailings dam failure that took place in Brazil in January 2019. And when I saw this failure, I immediately remarked, this is static liquefaction. It's a dreadful sight, quite shocking to see what happened there. It was a massive failure, and we will never forget what took place then, and it changed the world, and it brought about the GISTM. And that is one of the reasons why we are wanting to comply with it, is it has brought around a big change. Similarly, in 2015, it was the other Brazilian failure at San Marco, very large failure that resulted in the loss of 17 lives. And as a result of that, it also triggered a major need to improve what we're doing in the industry. When we started setting up this subcommittee to improve the document, we put together a team made up of people from the mining houses, consultants and specialists, operating contractor, universities, Minerals Council, SAIMM, SAICI, and SANS itself. And you'll see that the large majority of people there are consultants, and that's because it's a technical document and it needed the right level of input for all the different chapters. But it is quite a comprehensive team, and we felt that we had covered most things. Unfortunately, we didn't have a lot of representation from government, and so we're hoping that they do participate in the review process. In terms of timing, we started this document back in February 2021, and the first draft was put together by January 2022, and subsequent to that we held a workshop in February 2022 where we said, right, let's have a close look and make sure that all the changes we have made are aligned and that we're all talking the same language, because each chapter was put together by different teams. And by March 2022 we had a final draft, and all those who worked hard at this, there was some compensation for that, and funding was provided by Impala Platinum, so we thank you for that, and also by Sibanye-Stillwater. So we've reached the point now at May 2024 where we believe the editing process has now been completed by SANS itself, and we're at the point where we should be very close to releasing the document for public consultation. At that point, it's issued to stakeholders for review and public comment, and we then need to take those comments and incorporate them in the final document. That may take 2 to 3 months, and that should give us the opportunity to launch the final document in Q4 of this year. These dates are obviously subject to change, but that's our best guess at the moment. So you've heard about GISTM, and you may well ask, why did we choose to align with the GISTM in terms of the standard? We already had a good standard. Why GISTM, and why for South Africa? And it comes around the fact that we can't really accept a lower standard, and it would be very difficult to set a higher standard. We also don't want tailings dam failures in South Africa, so we need a good standard. Jagersfontein was a wake-up call. Investors and insurers will ignore us if we stick with the old document, so we may as well go with what is relevant and what is accepted. It's not going to, in my view, affect the mining industry detrimentally. Yes, it may well cost more to improve safety, but we will be saving lives, and I think that's the important factor. And similarly, if there is a tailings dam failure, a judge will just be asking, no matter where you are, what guidelines or practice did you use, especially when those things are available to us. So we feel this is the right thing to do to align. Things that we did consider when drafting the document was, should we ban upstream tailings dams? And we said no. We also looked at what some of the mining houses are thinking when they're saying, should we be setting targets or whatever for dry disposal for new tailings dam designs? And again, we didn't think that that was necessary. But again, one of the things we have put in the guideline is that you should be considering alternatives. And it shouldn't just be hydraulic deposition all the time. It should be new technology and so on. So what will the structure of this new document be? Well, very much the same as the old structure. They're both standards. We had aims, principles, and requirements, and we're going to follow the same structure again. GISTM has 6 topics, 15 principles, and 17 requirements, and in one way or another we have included all of them. We have not included legislation either. We did not think it was necessary to do that, and what we are doing is making sure that everything that you do then complies with local regulations. So we didn't particularly specify any of them, but that will be a requirement. We also didn't include any appendices like we did before. In terms of guidelines, there's lots of international guidance, and we would be recommending that everyone follows international guidance and local guidance. Some of the key changes that you will notice when the document comes out. The first is it focuses a lot more on affected communities, and a consultation process is essential now. And we already do consultation processes in our EIAs, and so that's nothing new. We do need to look very carefully at what the downstream impacts are to workers, residents, infrastructure, and so on. We need to make sure we plan accordingly. And we will be requiring emergency response plans as well as long-term recovery plans. Again, some of those were in place already, so it's not totally new. In terms of governance, there's a lot more jargon around, and you'll have got used to names like the accountable executive, the engineer of record, the responsible tailings facility engineer, the operator, the owner, and so on. And so there are defined roles and appointments. We need to now do a lot more training and make sure that people do understand what's going on the tailings facility. It's no longer just the plant metallurgist who's responsible for the tailings dam. He's going to need a lot bigger budgets and less interference from procurement. And that's one of the requirements of the GISTM, is that procurement doesn't override what technical people are saying is important in terms of safety. There need to be a lot more reporting processes, such as dashboards. There will be a lot more reviews and dam safety reviews. And the ITRB is the Independent Tailings Review Board. And, they will be playing a larger role going forward. Previously, we did do consequence classifications, but more in terms of environmental classifications and dam safety classifications. And now we need to do dam breach assessments in a lot more detail, using complex modeling, and this is an evolving science. We need to look at credible failure modes of how a dam might fail, how the water and solids flow out of a tailings dam when it does fail, what is the time of arrival, and what is the depth of flow in the different areas downstream. We need to look at what storm events might be happening at the time of the failure. And we also need to be able to plot these zones of influence and disclose that to the public and put in place alarm systems. Public disclosures are another big addition. Previously, mines did not need to disclose the safety of their tailings dams. Now they do. And then to what extent does this have to be disclosed? And there's guidance given around that. This is the table out of GISTM, where it talks about the consequence classification ranging from low, significant to high, and then to very high and extreme. And we talk about the PAR and the PLL, the population at risk, and the potential loss of life. And that is a key focus for any consequence of a tailings dam failure. Who is affected? And then, of course, we look at the environment downstream. what are the health, social, environmental, and cultural aspects that are impacted, and then what is the infrastructure and what might be the economic impact of a failure. Some of the key changes that we need to take into account when we're designing is what is the flood design criteria and what seismic or earthquake accelerations do we need to bring into the designs. And that's governed by the consequence classification. And you'll see you need various return intervals depending on whether it's low or extreme. Another key change relates to stability analyses. Stability is now fundamental to making sure that a tailings dam is safe. However, GISTM did not include any factors of safety. However, in the SANS code, we've decided to include some recommendations, and I'll go into the details of that. And this is similar to ANCOLD and ICOLD guidelines. We need to look at drained, undrained, and seismic analyses, and we also have included what we call the 10 rules for upstream tailings dams that need to be checked and evaluated. And that is because in South Africa, the majority of our tailings dams are upstream, and so therefore we need to apply those rules to our tailings dams. Just a reminder, we had the Cyclops tailings dam failure back in April 1993. It was an upstream tailings dam. Why did it fail? Because there was a high rate of rise and there was heavy rain. And that could have been avoided if the 10 rules had been applied. Similarly, if we go back to the Maritzburg tailings dam failure in April 1994, there was extensive outflow of tailings and water at that time, and this was what triggered the first version of the SANS code. 17 people died in that incident, multiple houses were damaged, and there was environmental damage as well, and this could have been avoided if water hadn't been stored on the facility, which would have meant that there was a high phreatic level at that time, and there was no freeboard. All of that could have been avoided if the 10 rules had been applied. So this is a process flow taken out of the document. And what we are doing here is we are suggesting that this is a way in which you could analyze stability. A bit of a rule-based approach, but it helps everyone to follow the same type of approach. It's not prescriptive, but it is useful. And so it says if you start off with looking at drain factors of safety, if you exceed 1.5, you can proceed then to look at undrained factor of safety. If that factor of safety is greater than 1.3, you then proceed to look at the factor of safety for liquefaction. And if that exceeds 1.1, then you should have a safe tailings dam. If any of those are not met, then you need to follow a process where you look at the probability of failure for the drained factor of safety and say, what can I do to make sure that I don't have steep slopes, I don't have a high rate of rise, I don't have a high phreatic level, what am I going to do if there's a clay foundation, and so on. And there are different things that you can look at to make sure that you understand what are the things that could increase the probability of failure and how do you address them. In terms of the undrained factor of safety for the peak strength case, you need to then determine the probability of triggering. Is it a seismic event? Is it a flood event? Is it a high rate of rise due to high tonnages? Is there a possibility that a sinkhole forms? Could it be a penstock failure? And if you've identified those triggers and you can control them, well then maybe you can accept a factor of safety that is low. If you can't, then you need to take remedial action. And then lastly, if you then find that for the liquefaction case, you have a factor of safety less than 1.1, then you need to look at the exposure or reduce risks. And what do you do in that case? Can you add redundancy to the decant system? Do you need to build a buttress? Do you need to flatten the slopes? Can you divert inflows to the tailings dam? Do you need to relocate people or put in protection berms or move infrastructure? So these are all things we can do to try and mitigate low factors of safety while still accepting that that might be a safe tailings dam. And in line with that, requirement 4.7, which falls under topic 3 and principle 4 in the GISTM, has this clause here, and I'm going to read 4.7. And it talks about existing tailings facilities. So it's not always easy to retrofit these stability requirements to those existing tailings dams. And it says there, existing tailings facilities shall conform with the requirements under Principle 4, except for those aspects where the engineer of record, with review by the ITRB or a senior independent technical reviewer, determines that the upgrade of an existing tailings facility is not viable or cannot be retroactively applied. In this case, the accountable executive shall approve and document the implementation of measures to reduce both the probability and the consequences of a TSF failure in order to reduce the risk to a level as low as reasonably practical, what we call a LAR. The basis and timing for addressing the upgrade of existing tailings facilities shall be risk-informed and carried out as soon as reasonably practical. So what this is saying is that for existing facilities, they may not comply to all the rules, but we can, under certain conditions, with agreement between the parties, accept lower factors of safety. And so we've allowed that. So we're not saying that in all cases, all factors of safety have to be complied with, but that does not mean there's a piece of elastic and you can stretch and abuse it. So we need to put risk management measures in place. So this means we need to look at the failure modes and effects, and that can be done by bow tie analyses. We need to look at the critical controls and what we call trigger action response plans. And many of you might have been exposed to that already, and you make sure that you know whether it's the freeboard that is one of your critical controls, or the piezometer levels, the drainage rates, movement around the tailings dam. All of these need to be monitored. And of course, now we're moving into real-time monitoring. So where these factors of safety are not achieved, the LAR is allowed, which is the risk and informed approach. But as I said, this is not a justification for unsafe tailings dams. Action plans must be in place, and they must be put in place within the right time frames. We are going to require more rigorous monitoring, and you must have an evacuation plan in place because you've got a potentially less stable facility. Other key challenges that we need to face up to when adopting the new code is that for any new design of upstream tailings dams, this is allowed, but all these stability requirements should be checked carefully, in particular because we're designing them with barrier systems in many cases which have low friction properties. We also have to take into account these large storm events in the design. It could be anything up to the 1 in 10,000 year event, and these are very large events, particularly when we're talking about 1 in 10,000 year earthquakes as well. So be wary of that. It does make the designs more conservative, but that will be safer. We have moved into a situation where monitoring by means of real time has arrived. And this is what we need to now make sure that we have implemented. The technology is there, so we can't ignore it anymore. We have to work out what's best for our facility. It does mean that you've got to have new people on your TSF team. You need IT people, you need CNI people. The IT people need to make sure that that data is collected and can be plotted on your dashboards, and that you've got alerts and triggers in place. The CNI guys need to make sure that your instrumentation is working properly, whether it's batteries, whether it's data loggers, whatever it is, they know how to maintain those systems. We do have a problem with theft and vandalism, and we need to make sure that that's taken care of as far as possible, because we don't want false alarms. we need to make sure that these systems are maintained and working well. We are going to need more resources to make sure that these tailings dams are compliant. It means there's a lot more work. And I'm finding this a much more stimulating career path with all these extra things that we have to do. But there aren't enough skills in South Africa. There aren't enough consultants. And there aren't enough people to work for the owners' teams and for the contractors to make us more professional. So we have to do in-house training, and we have to improve competencies, and that includes the regulators. We need to make sure that we have the right resources, and as I said before, procurement needs to be in line with that. We may also need quicker decision making, because some of these things need to be put in place sooner rather than later. We are going to be reviewed more, and that's the place of the independent review boards and the dam safety reviews, and they need to be done at regular intervals, and they can be very constructive, and they can lead to us coming up with good solutions. Tailings dam closure is something that we haven't done well, and GISTM prescribes that we should be putting feasibility level studies in place, and so the SANS code is basically saying we should be doing the same thing. It's not easy to close a tailings dam, and certainly not easy to make it a sustainable closure. So we need to work out what are the final land uses, what is an acceptable side slope, and what are we going to do in terms of vegetation cover and so on, particularly in more arid environments. So in terms of timing, you already know that the August 23 deadline is passed for the very high and extreme consequence classifications. So these timelines apply to the ICMM companies. So with Impala not being an ICMM company, I know that committed to similar deadlines. So this may have already been met. And so August 2025 is the next deadline that was set for the low, significant, and high classified TSFs. And so I think Impala is well on the way to making sure that they are compliant, and I think that's exhibiting good practice. Some of the delays may be due to things like skill shortages, and certainly things like laboratories are not able to keep up with all the demand on them at the moment to meet those timelines. When the SANS code, the new SANS code is issued, we expect that to also be rolled out in a similar way, where if say it's rolled out at the end of this year, companies will be given 3 years to become compliant for the very high and extreme facilities, and they'll be given 5 years for the low, significant, and high classified tailings dams. So moving forward then, we believe that SANS has been superseded and that we should align with GISTM. If it is rejected for any reason, we would probably then bypass SANS and still have it published as an industry document, either through SAICI or the SAIMN. So we would suggest that you should be preparing to be compliant, which is the case in Impala's case, and that you should be encouraging your consultants to design and analyze accordingly. We need to make sure that government bodies are on board as well, and this will be beneficial to all parties. And lastly, I like to leave you with this slide that is the aftermath of the Brumadinho failure. We basically say, let us never forget what happened there. It didn't happen in this country, but please let it not happen in this country. If we do things right, we obviously can do things better. So that's the last message from me. Thank you for your time. Thank you for listening, and apologies for not being with you in person and answer any questions. But I trust that this has been worthwhile. So thank you again, and good night.
Okay, thank you. It was insightful and fantastic to see what's happening in the South African space on tailings management. Okay, so we are a bit behind schedule, so So we are going to go back to Enzo, who I introduced earlier.
Sorry.
Yeah, he's had some network issues the previous time. And we are really glad you can join us. I've read your CV to the others if you haven't heard it. So you have been introduced, and we are looking forward to your presentation. So this is a live presentation again, so we can have questions and answers afterwards.
Okay.
Thank you.
You're welcome. Can you hear me first of all?
Yes, you hear me
Perfect.
well.
I will. Wait a moment. I will share my presentation.
Enzo, do you have your presentation open on your computer?
Yes.
Okay. So if you go to the bottom, there's a little green icon. If you just press share.
It is what I'm doing, but I don't see my presentation on the screen. We wait a moment that I will try again, share, Windows, and it's not there. Okay, let's do it this way again. Let's try this way. I reopen it, and that's it. Can you see?
We can see it. If you can just put it into presentation mode, Enzo.
Can you see in the presentation mode now?
No, not yet.
Share the screen. Windows. I think you can see my presentation now. Yes.
We can see it, but it's not in presentation mode. If you just
Hello.
Hi, Enzo. Can you hear me?
Is now in presentation mode?
And not yet, no.
But if I now for me is in presentation mode. Wait a moment that I will try to. I cannot share the entire screen according to the Microsoft Edge tab.
Wouter, I think while Enzo's getting his presentation ready, okay, let's just see now.
Can you see?
Yeah, we can see it, Enzo, but it's not in presentation mode. Okay, there we go. If you can just put it in full screen.
Here, now, is in presentation mode.
Yes, you can present from there, Enzo, but we can see your notes at the bottom.
Oh, I can cancel that. Okay, I would cancel the note, but I don't know why I cannot see in the presentation mode. Wait a moment, if I do in this way. Okay. Let me know if it is in presentation mode now. No.
Now check there next to the. Okay, you can just share your PowerPoint again. There on the top in the orange strip, there's autosave off, the stiffy back, forward, and then there's a screen with a play thing in it. With a try just up with your mouse. Now go up into the orange strip. Yes, okay, to the right. To the right. Yes, that one.
Okay, thank you very much. is now in presentation mode, I suppose. Okay, first of all, I would thank you very much to give me the opportunity to present the Tenova way to valorize the slag to the dry granulation process. And in particular, we will have a look on Tenova experience on electric arc furnace and ladle furnace slag. Which is the slag dilemma. First of all, it is how to valorize the slag, which is the main byproduct or product of our reactor, in particular pyrometallurgical reactor, and which are the way to handle this kind of possible new raw material, because nowadays, especially for electric arc furnace and ladle furnace slag, we have trouble in manage this kind of byproduct. In particular, in the electric arc furnace slag, it is the management of the slag pit, because temperature of risk of the explosion in case we have the mixture within slag and water, or in case we have cold water in contact with the slag, we have the leaching of heavy metals and the big dilemma on how to dispose the water. In case of ladle furnace slag, which has a crystalline morphology, we are facing to disintegration of the ladle furnace slag with a big problem of logistics. The ladle furnace slag is classically becoming really fine powder that is really difficult to manage in terms of cost of the handling and the possibility to separate metals and mineral fraction in order to try to valorize. The basic result it is that these two materials nowadays mainly disposed into the landfill, having a problem in terms of sustainability of the steel production in this case. I think this trouble it is common to many other metal production, and for this kind of yes.
Just sorry to interrupt. Your slides are not moving on our screens.
Yeah.
We'll see if we are still seeing your first slide.
Can you see me?
I can see you, yes, and I can see your first slide in your PowerPoint, but I have a feeling you're further along. There we go. Thank you.
Can you see the slide?
Yes, I think you could just present like this. I think then continue with your slides. But yeah, because with your slides down.
Okay, it is for this reason that Tenova since 2017-2016 developed the technology based on the forced air slag granulation with an European patent, which permitted the ultra-fast cooling of the liquid slag, both ladle furnace and electric arc furnace slag, of the liquid slag, forced through the blowing of forced air, in such a way that we can obtain mineral fraction and metal fraction of this slag in solid form and in dusty phase. The rapid solidification will permit to obtain a glassy amorphous material, and in particular this will become more interest for the construction industry as a new possible raw material for the slag. We avoid the dust production, reducing the cost of the slag handling because we avoid the disintegration, and we stabilize even the element, avoiding leaching, in particular with the case of the heavy metals. The dry granulation will permit also to avoid the use of the water, which allows to avoid the emission of gaseous pollution that it could be toxic for workers and further people that is working in the surroundings of the slag management. The valorization of the slag is a consequence of this new treatment, and the valorization of the slag will clearly reduce the greenhouse gas emission of the overall steel steel production process, preserve landscape, reducing the raw material extraction, because we want to reuse the slag into the mainly the construction industry, and we also reduce the soil consumption because we avoided disposal into the landfill. Now we are moving to the technology. We developed two different technology for the forced air granulation. The first one is the so-called online EAF slag online technology. In this
Enzo,
case,
just advance your slides on our screen as well, please.
now you can see.
You're on slide 2, so we see the forced air slag granulation.
Okay. Okay, this one it's I have to repeat this one. Okay, Tenova developed this forced air slag granulation, and we obtained a patent in since 2017 in order to perform a methodology for the full ultra fast cooling of the liquid slag through forced air in order to obtain a rapid solidification for obtaining a glassy amorphous material that can be reused in the construction industry, avoiding dust production and reducing the cost of those slag handling because we avoiding the disgregation of the slag. Through this methodology, we stabilize the element, avoiding the leaching, and also we avoid the use of the water because we are cooling the slag through only forced air. Avoiding the water, we permit also to avoid emission of gaseous pollutants that could be emitted by the treatment of the water with the slag, driving a more safety operation in the slag management. All this treatment will drive to a valorization of the slag to be used as construction material, reducing the greenhouse gas emission on the overall metal product extraction for new raw material for a construction industry. And also we reduce the soil consumption because we avoid to dispose onto the landfilling. I changed the slide. Can you see the slide changed?
No, I think take it out of presentation mode on your side because we are not seeing where it is.
Yeah.
So now we see the right slide.
We have to, yeah. Then it is in this way. We have to manage. Okay.
Yeah,
And
so,
then I will.
yeah, do not click there. You just take it through as it is. I think it's safer.
Allora, I will. Can you see now the complete slide?
Yes. Yeah, so we're on slide 3 now.
Okay. Now is slag forced air granulation. We have a look onto technology. We developed two different technology. One online methodology for the slagging, where you can see that the nozzle of the fan or the blower, you have Can you see slide 3? Okay, sorry, gentlemen. Can you see slide number 3? In where you have the fan nozzle below the reactor. From the reactor, we have the pouring of the foamy slag, that is of the foamy and liquid slag, that is impacting on the granulate, on the blowing air, performing the slag granulation. These technologies developed at industrial pilot and the slag treatment obtained in this application under the electric arc furnace. And here an example of the powder that we obtained, which has an amorphous fraction approximately 90% with an index basicity to more than 2.2. The second methodology is the offline EAF slag. In this case, the ladle is taken into the slag granulation station, where located in order to blowing the liquid airflow, which is onto the airflow, which is flowing in order to stop the airflow, the liquid flow in order to the granulate slag process. In this case, the ladle is on a crane. We are developing a tilter, that a tilting mechanism that is moving this kind of ladle. This is the material obtained. This is ladle furnace slag that has a silica content that it's around 20%. For this reason, we obtain this kind of green material. I moved the slag. Can you see the slide 4?
No, Enzo, we can't see slide 4. Okay, we can see it now. Yes, we can see it.
Okay, I will perform again in this way.
We can see
Now,
your slide,
you see
Enzo?
slide 4?
Yes, we do.
Okay, then is okay, the complete slide. Okay, this process is managed through a, let me say, is the result of a methodology developed of Tenova that can be applied to multiple kind of slag. We have the methodology consists in many further steps. The first one is the definition of the chemical property of the slag at different temperature in order to define which is the correct flowing amount of flowing air and pressure needed for performing the slag granulation. Performing the slag granulation, then defining the working point of the fan that has to granulate. It is a CFD study in order to study the primary breakup of the liquid flow to the slag. That means to understand which is the exact amount of air needed for break up the liquid flows in order to form a droplet, and also to define the amount of air into balls. The ball study in terms of cooling effect from most, let me say, liquid and heat. I'm not going to say liquid, but most double phase liquid and solid internal of the ball, in order to define which are the timing needed for solidify the balls. Once the grains is solidified, we can understand which is the layout. That means based on the timing of the timing needed by the grain to become solid, we can manage which is the impinging wall distance for and define which is the correct flight time of the drop in order to become solid, in order to understand which is the layout needed for and the space needed for this technology. Then we are moving to the phase of testing or pilot, small plant, in order to testing our process, and then we can even perform different testing on site. Now I will check sharing, and then we are moving to slide 5. I suppose you can see my slide number 5. Okay, here it is. Yes. Just to say that since 2017, Tenova started up several industrial testing facilities in the world of steel. We have technology applied in line, where you have, as you can see here, let me say, it is a automatic tilting device applied a slag pot in order to perform the slag pouring, or we have, as in this case, the case of a liquid flow that is broken by a fan. In this case, the slag is moved by a crane. Different condition for different kind of slag and different grain solution. Just to have a look on some of the result that we obtained is here. Some of the result is represented on slide number 6. In this case, is the dry granulation of EAF slag. In this case, we can see this is the result on industrial testing. What you see in the slide 4. Through X-ray diffraction, we can measure the morphological analysis, which show that the amorphous material is more than 90%. What is important to say it is the chemical composition of the slag is not changed, was not affected by the airflow. In this case, I would say that in case of the electric arc furnace slagging, where we have the high content of FeO, the only effect it is an increasing of FeO in terms of increasing of oxidation of the ferrum oxide, moving from FeO to F2O3, but the fraction of the overall ferrum oxide is not changing with respect to the amount of let me say steel available in the ladle. What we can say is that with respect to our methodology, the previous grain size, we obtain a consider between 0.5 and 1 millimeter instead of more than 1 millimeter, because in case of the slag from electric arc furnace, we are in reality B-phase liquid, in where gaseous and the liquid slag are combined because of the foamy nature of this slag. I will move to slide number 7. Then it's a new share, and then Windows. We learn any things. And then it's slide number 7. It is related to the result of more relevant result for us. We can see that practically the amount of the composition of the slag was not changing, and even we have a really good comparison between the calculated the simulation, or let me say the granulation the grain size calculated by our simulation system and the grain obtained by during the process. Even we can obtain more let me say glassy texture. This is because even it is even because the amount of silica or the silica oxide available into the slag. The granulometry is changing between 0.5 and 3 millimeter, expected as we calculated. To the relevant technology, or the technology that we are developing. Now we are looking at this one. It is quite important to say that through this methodology, we really find a way to valorize the slag. What does it mean? That once the slag is produced into the steel shop and the ladle is transferred to the granulation station, we obtain the grain, and after proper cooling, we can separate the metal fraction through deferrization, where the metal fraction can be reutilized into the reactor, while the mineral fraction can be or sold to the customer, as example for as new raw material in the construction industry, or it can be also, in the case of the electric arc furnace, injected into the electric arc furnace as lime substitute. This is the two possible user that we nowadays find that we are developing here in Europe. Can you see slide number 10? Or you still see number 8?
No, number 8 now. There we go.
Okay, and then I move new share. Okay. Share. And then it's slide number 10.
Yes.
Let's see here. This is the first plant that we are developing here in Italy. We start in Q4 2024. You can see that we have a tilter for dedicated to perform the slag granulation, the system heater in order to maintain the ladle, the processing ladle heat, because you know in the electric arc furnace we have batch processing. We have a big granulation chamber in order to avoid that anybody can be injured by the flows of slag and air. We have the connection to the existing fume treatment plant. The air used for the granulation has to be treated in the main dusting system. Here on the right, you can see the tilting mechanism we are developed for this kind of technology, together with the nozzle of the fan, where for pouring, for performing the blowing of the system. We are going to the last slide, which is slide number 10, new sharing, and then some conclusion. It is that developed a methodology for a technology for the dry granulation of the electric arc furnace and electric furnace slag. The process of forced air slag granulation is developed through industrial testing and computational modeling of the slag, and will permit really fast cooling in order to obtain an amorphous morphology higher than 90%, that will permit to valorize the slag into the as raw material into the construction industry, reintroducing the slag into the circular, into the economy. Tenova is developing the first installation of the industrial plant that will start in Q4 2024. I would thank you very much. I would excuse for the difficulty, the technological difficulty that we had today, and I'm available for questions or opinion or answer.
Hey, thank you very much, Enzo. Yeah, I've been dropped off a couple of times. I'm not sure what happened to my Zoom. I'm not seeing any questions in the question and answer pane. So if we're getting any, we will email them to you to answer in your own time. Then thank you very much. We appreciate your time. Okay. Thank you very much. Then I'm going to Nestle, just a quick check. And you still hear me at least?
I can hear you clearly, Wouter.
Okay, fantastic. It was just on my side. Okay, good. So so we get to the last presentation of the day, and back to tailings. Right. So I'm going to introduce then Hendrik Otto. So Hendrik, or see Hans, I'm not sure that's his noemnaam. He's a professional engineer at WSP, based in the Reading office in the United Kingdom, and has served as a mine waste practitioner at WSP Golder since 2011. And prior to that, at SRK Consulting in Johannesburg. During this time, he has fulfilled various TSF monitoring, design, CQA, and project management roles for mine waste and tailings-related projects in Europe, Africa, and Asia. Hans has extensive experience in the field of risk management and is currently assisting a number of mining clients who are working towards meeting the requirements of the global industry standard in tailings management, GISTM, since the publication of the standard by the ICMM in 2020. Okay, so he's going to present on the evaluation of legacy tailings storage facilities using a fault and event trees analysis approach to assess failure modes and a sensitivity analysis to identify and prioritize remedial action. Thank you.
Good day, ladies and gentlemen. I'm Hans Otto, Associate Tailings Engineer at WSP UK Limited. Thank you for joining me for this presentation on the evaluation of legacy tailings storage facilities and using a fault and event tree analysis approach to assess the failure modes and sensitivity analysis to identify and prioritize remedial action. Just a bit of an introduction. If we kind of look at the historical background of tailings storage facilities, these facilities has always has historically been seen as a necessary evil and has, as a result, been done as cheaply as possible. Cost cutting has led to poor design and/or construction and/or operation of many of these facilities, with which led to many TSF failures through the years, with tragic consequences for human life and the environment. One of the positive outcomes of these failures has been the development of the global industry standard on tailings management by the ICMM, the United Nations Environmental Programme, and the Principles for Responsible Investment. Unfortunately, there are still thousands of closed and abandoned TSFs, often located in poorer countries, that pose unacceptable risks to the public and the environment. The polluter pays principle doesn't work where the mining companies are long gone, and dealings with these legacy facilities becomes the responsibility of governments in the countries where they're located. There are often limited resources, human and financial, available to address these legacy issues. We're going to look at global and national initiatives and national capacity to address legacy sites. On the global and national initiatives, we have got the UN Environmental Programme, the EU Mine Waste Directive, and there's also other initiatives in progress in Australia, the United States, Canada, and China. National capacity to address legacy sites include or requires awareness, sustained capacity, including resourcing, and effective government structures, including effective regulation of mines. Many vulnerable countries are heavily dependent on mining. It is thus essential to find the right balance between governments and industry in allowing national development to take place, whilst making sure mining companies take responsibility to safeguarding people and the environment now and in the future. If you kind of look at the evaluation risk by any tailings facility, we need to start with the consequence classification. The Canadian Dam Association considers incremental losses of TSF failure to includes evaluation in terms of population of risk, loss of life, loss of environmental resources and values, and environmental losses. The GISTM consequence classification uses a very similar approach. If we kind of look at tailings facilities in general, and we look at there was quite a good paper prepared by Lararli and Lull in 2017, and they basically evaluated tailings failures in the period 1915 to 2016. If we kind of look at the failures by type, earthquakes were quite prominent, erosion, foundation failure, mine subsidence, overtopping, seepage and piping failures, slope instability, structural, as well as undefined, quite a number of undefined failures. Causes of failure can relate to faulty design, construction, poor management of events, and a combination of these factors. If we look at risk assessment, risk can be defined as the probability of failure multiplied by the consequence of the failure. And that has led to the development of this typical kind of example of this table above, with the consequences from minor to catastrophic on the x-axis, and the likelihood from almost certain to category A to E, category E, which is deemed to be rare. If we look at site-specific potential failure mode and effect analysis, these can be developed for TFCs to identify unique failure modes that qualitatively weight the likelihood and consequences of factors with the potential to contribute to a failure. Risk for engineering purposes must incorporate both probability of failure as well as the consequences of the failure, and that leads us to that risk classification that I gave to you earlier on the slide. If you look at risk assessment, just a short introduction, we've got a top fault, which is an undesired effect under investigation and risk analysis. That would be failure of the TSF with the release of tailings. Then we look at events or situations that may give rise to the top fault. I think it's important to note that generally a failure is never due to a single factor. There's usually a number of contributing factors. And the top fault and events can be presented by the trunk and branches of an event tree. It is called a fault tree when the probabilities associated with each of these events have been entered. Then we can look at the Boolean algebra, and that can use and or gate logic in tree scenarios, allowing for the calculation of probabilities of failure or various failure modes for often complex systems. It's quite interesting. This was, I think, originally developed by NASA and then also found kind of applications in the nuclear industry, where many of the risk assessment kind of tools were originally developed for. We get dependent causes, which is an AND gate, and it means those the factors should occur simultaneously to give effect to a particular hazard. A joint probability for n number of dependent causes, P would be P1 multiplied by P2 multiplied by P2 multiplied by all the other factors until you get to Pn. And then if you look at independent causes, which are presented by an OR gate, these are called independent of its occurrence and gives effect in giving effect to the hazard. A joint probability for n number of independent causes is 1 minus the probability, 1 minus the first probability multiplied by 1 minus the second probability multiplied then with all the factors until you and then finally by 1 minus the final probability of Pn. If you look at risk assessment, event trees become a fault tree by assigning the probabilities based on the data interpretation, analysis, comparisons with published literature, and engineering judgment, including using the mapping table for probabilities presented by Williams and Chapman 2019, presented in the table below. You can see that basically if you kind of look at a probability of 1 in a million, the likelihood is deemed to be almost impossible or implausible, or there is no published information on a similar event. Whereas if we go down to probability of 1 in 1,000, it's deemed unlikely, recorded recently elsewhere. And then if we look at certain, that's obviously or as near to, it makes it no significant difference. That would have a probability of 1. An important contribution by Silver, Lamb and Marr was made in 2008 by a paper which basically presented a kind of a link between the factor of safety on the x-axis and the annual probability of failure depending on the quality of construction. The blue line you can basically see is basically best quality construction. So for a specific factor of safety, you've got a relatively low probability of failure, whereas with some of the other factors, category 1, 2, or category 4, which would typically be an example of which would be a typical farm dam without a spillway, would be a category 4, which is presented by the yellow line. There was a simplified hypothetical analysis considered in this paper. The undefined tailings storage facility failure type and earthquake failure presented in figure 1 were not considered. 3 failure modes were considered only: overtoppings, failure, slope instability, and seepage and piping. An unlined closed abandoned TSF was considered, developed using hydraulic deposition upstream construction methods, typical of the ones we've seen used in Africa or Southern Africa during the second part of the 20th century. The closed TSF is equipped with a closure spillway. No intervention is taking place to compromise freeboard or slope stability or compromise internal water management. It is assumed that the facility is located in an area of low seismicity, and the potential risks associated with static or dynamic liquefaction were not considered. This is basically just done to limit the scenarios to be considered. Factors considered in the sensitivity analysis for the base case fault tree included erosion damage to the crest of the facility, storm event in excess of the design return period, stormwater diversion failure, closure spillway failure, decant failure, static slope failure under normal conditions, static slope failure with a raised phreatic surface, drainage failure due to seepage, drainage failure due to piping, and filter failure. After populating the fault tree with probabilities, some of the values were modified slightly so that we ended up with the probability of overtopping failure to be greater than the probability of slope failure, and that being greater as the probability of failure due to seepage and piping failure, as calculated as presented in the paper by Larauri and Lull in 2017. Basically, just to keep things in a little bit more of a perspective based on historical failures. For the sensitivity analysis, the approach used was to analyze the factors that contribute to TSF failure and the effects on the 3 fault modes considered. Each of the factors were considered individually. The probability of occurrence of a specific factor under consideration was increased by 1 order of magnitude, whilst keeping the probabilities for all other factors unchanged. The effect of the change to the specific factor on the probabilities of failure for overtopping failure, slope failure, and seepage and piping failure were then recorded. These probabilities were compared to the probabilities of failure calculated for the base case. This was done by dividing the newly calculated probability by the original base case probability for the specific failure mode. This is basically just an example of the failure or the fault and event tree considered. You can see basically the main branches for catastrophic failures: overtopping failure, slope failure, and seepage and piping failure. I think I'm not going to go into more detail, but it is described in the paper that I presented at the Tailings Conference last year in October. If you kind of look at the base case for overtopping failure, that's a combination of inadequate freeboard and water accumulation on the facility. Inadequate freeboard can be due to no intervention, or if the freeboard can be compromised due to erosion damage to the crest, static settlement, or dynamic settlement. And if we look at water accumulation, that can be a combination or would be a combination of excess water on the TSF and an inability to remove the water. The excess water can be a result of a storm event, in excess of the design period, or stormwater diversion failure. And the inability to remove water can be due to closure, spillway failure, or gravity decant failure. If we look at slope failure, that can be due to no intervention, an embankment failure, or a serious embankment failure. Then we can also have embankment failure as a result of static slope failure with under normal conditions, static slope failure under raised phreatic surface, or dynamic slope failure. Then if we look at seepage and piping failure, there can be serious seepage or piping issues and sustained high phreatic surface in the facility. And those are the contributing factors that can lead to this failure mode. Factors not considered in the sensitivity analysis are indicated in red, and that would be things that's hard to quantify, including, for example, the possibility of an unknown water source that contribute to water buildup in the facility, i.e. a fountain underneath the tailings storage facility. The end result of this, these kind of fault inventories that were developed and analyzed was basically the following table, which has got factors that were kept constant, which you can see in the top number of lines, and then factors that were evaluated. The factors evaluated were evaluated one at a time after increasing their probability of occurrence by 1 order of magnitude from the base case to actually see how big an effect it has on the overall probability of failure. And as you can see here, if you kind of look at the kind of light blue cells, it was found that if we look at probability of overtopping failure, the factors that played the biggest role or potential role with that was basically looking at erosion damage to the crest. Another factor that played a potential big impact or role, or might have a big effect, it's quite sensitive for, is basically a storm event in excess of the design return period. And the third factor identified for this failure mode was the effect that a potential gravity decant failure could have on the failure mode. If you look at the probability for slope failure, you could basically see that the factor that was identified was raised phreatic surface. That plays quite a critical role in that failure mode. And if we look at the probability for seepage and piping failure, the factor identified there to be, or for the stability of the facility to be quite sensitive for, that was identified as a storm event in excess of the design return period. So summary and conclusions. Using the CDA and GISTM's approach should be the first step when evaluating any closed or abandoned TSF to identify and prioritize facilities posing the greatest risk to the public in the environment. Failure modes of the TSF, including closed facilities, can be very complex, and to develop site-specific fault inventories, the persons responsible requires intimate knowledge of the facility and its credible failure modes. And fault inventory analysis can be used to evaluate credible TSF failure modes identified by other risk assessment methods, for example, potential failure mode and effective analysis, to assess the individual factors or events that contributes to specific tailings failure, specific failure mode. By assessing the sensitivity of various factors or events and their potential effect on the probability of failure, it is possible to identify factors that may be critical to the safety of the system. These factors should form the focus of remedial actions to safeguard the safety to safeguard the long-term safety of these facilities. Thank you very much for your attention. If you've got any questions, you are welcome to email me at hans.otto@wsp.com, and my apologies for not being able to present this directly to you today. I hope you found the presentation insightful, and I'm looking forward to receiving some questions from you. Thank you very much.
Okay, thank you to all the presenters in their absence. Thank you for SAIMM for putting this together. Thank you for everyone who has nominated some of the presentations that was given today from the past SAIMM presentations. Sorry it went a little bit over. We are still in the, I think, scheduled time at least. We just have shorter time for closure for this reconference. Thank you for everyone who is still online and to have been online during the session. We appreciate it, and yeah, our comment or all the questions and so on will be sent to the presenters, and we'll get the answers back for you as quickly as possible. And I'm hoping you learned something. Adele, if you are online, you have some closing comments.
Yeah, thank you, Wouter, and thank you for chairing a very difficult session, I must say. And we do apologize. Sometimes we can't help for technology that's not playing the game, specifically if we're streaming from Italy, then it's a different story. But yeah, we survived, and we listened to all the presentations, and thank you again to SAIMM for arranging this. This is value to our doorstep just there. And as we started, hopefully each one of you can take something from this conference that you've learned. I definitely did. I made quite a few notes. And take this, apply in your sections, or just for yourself as a learning. It always helps. I think just last thing from my side is, if you are not yet a SAIMM member, then you need to question yourself because it is so easy to become a member, and it is so valuable to your career, your knowledge, and your growth. Go to the website, click on the button, member. I want to become a member, and then complete the forms. As easy as that. So please do that if you're not yet a member. The doors will open, you will have access to many platforms, and you will be able to enrich yourself. And if you have questions, even if you're in your own discipline and you don't have the answers, there's a huge library that you can go and search for answers. So please do that. It's not going to cost you or your operation 1 cent. This is included in our corporate partnership with SAIMM. So please do that, so that we get you on the membership list, so that we can walk this path together with SAIMM. We will have another conference, or as we call it here, a reconference webinar, closer to year end. And we will do it in a slightly different format. We've had a quick discussion, myself and Wouter, this morning. We would like to bring more subjects or disciplines to the table, and we will do it in that format, the next one. So please look forward to that. And if you have any suggestions or ideas how we can do this differently and better, please speak up, so that we can incorporate your ideas as well. This is not my conference or SAIM's, a reconference. This is ours, and we need to benefit. And if you would like to see something different, please let us know. We can surely arrange whatever you need through SAIMM. So thank you again, and thank you for everyone that participated and stayed until the end. And with this, we are now 1 o'clock on the dot. Well done, Wouter. And we will then close this this morning's webinar. Thank you again, and good luck. A few weeks till year end, and yeah, we're going to have a good new year. I'm wishing you all a good new year, if I can say it like that, 2025. Thank you, and goodbye.
Bye, everyone.